Tonight, as you settle in, as the world outside softens its edges and the rhythm of your day gives way to the quiet cadence of your breathing, let's begin a gentle exploration. There is no need to strive for understanding, no pressure to arrive at any destination. We are simply here to wander together in this quiet space. The weight of your body is held, supported. The air you breathe moves without effort. And in this stillness, let us pose a single, elegant question, not as a problem to be solved, but as a door to a place of immense and quiet scale. What if we lived on the sun? Let the question hang in the air for a moment. Not as a fantasy of impossible technology, not as a challenge to physics, but as a thought experiment, a way of seeing our own world from a vast and clarifying distance. We are not imagining a journey through space or the construction of some impossible shield. Instead, we are asking what it would mean to exist in a place of pure, unmediated source, a place without shade, without dawn or dusk, without the gentle filters that make our own lives possible, a place where the full, unfiltered truth of a star is the constant environment. By imagining this impossible reality, we might just come to understand the quiet, intricate, and often invisible systems that hold and protect us here, in this room, at this very moment. This is not a story of survival against the odds. It is a story of appreciation. It is a slow, unfolding meditation on the nature of home, written in the language of geology, biology, and the steady passage of deep time. We will not be battling solar flares or cosmic radiation. We will be walking through a landscape of ideas, noticing the subtle architecture of our world that allows for things like coolness and slowness and sleep itself. The sun in our journey tonight is not a destination. It is a lens. It is a symbol for the raw, untempered universe, and by holding it gently in our minds, we can begin to see the subtle, profound, and life-giving ways our own world says, not yet. More slowly, rest here. There is no test at the end of this journey. There is only the quiet comfort of the blankets around you, the gentle rise and fall of your chest, and a deeper sense of the intricate grace that makes this simple moment of peace possible. So let your mind drift. Let the curiosity be light, like a feather on the breath. And let us begin. Before we drift too far, let's agree on the gentle rules of our shared thought experiment tonight. Our purpose is not to find a definitive answer because our question is not a scientific one in the traditional sense. It is a philosophical tool, a key to unlock a different kind of seeing. When we ask, what if we lived on the sun, we are setting up a contrast. On one side, we have the sun, a place of immediate, overwhelming, and constant energy. It represents a system with no buffers, no delays, no memory. It is pure, unfiltered cause and effect, happening all at once, everywhere, forever. On the other side, we have our world, the Earth. And our method tonight will be to explore the Earth not as a separate entity, but as a system of mediation, a system of buffers, delays, and memories that stands between us and the raw power of the cosmos. We will proceed with a spirit of inquiry, not certainty. Think of it as walking through a vast, quiet museum after hours. We are not here to debate the labels on the exhibits. We are here to notice the relationships between them, to feel the resonance of the entire collection. We will look at scientific models not as absolute truths, but as provisional maps, sketches of a territory far too complex to ever be fully captured. We will use these maps to guide our attention, to point us toward the vast, interconnected machinery of our planet. We will talk about feedback loops, geological time, and the chemistry of the atmosphere, but we will do so gently, always connecting these grand ideas back to the simple, tangible reality of your own felt experience. Our guardrails are simple. We will avoid hype and catastrophism. The point is not to feel fragile, but to appreciate resilience. We will resist the temptation to assign intent or purpose to natural processes. A system that regulates itself does not need a plan. The regulation is an emergent property of its interconnected parts, like the way a flock of birds moves as one without a leader. We will honor the complexity of these systems by acknowledging what we do not know. Uncertainty is not a failure of understanding, it is an invitation to remain curious, to stay open. And finally, our ultimate goal is not intellectual mastery, but a deeper sense of belonging. The systems we will explore are not external to you, your breath, your body. The very atoms that make you up are woven into this planetary tapestry. So, our inquiry is in the end a form of quiet self-recognition. We are setting these guardrails not to limit our journey, but to ensure that it remains a restful one, a journey that allows the mind to wander freely and safely, knowing that the path is held by a clear and gentle purpose. We are here to explore with no expectation of a final conclusion, content to simply notice the intricate beauty of the world that holds us. Now, before we venture outward to the scale of planets and stars, let's begin right here, in this room, in this moment. Bring your awareness to the physical space you occupy. Feel the texture of the fabric against your skin, the smooth coolness of a sheet, the soft weight of a blanket. These are not abstract concepts, they are tangible realities. The weight you feel is the simple, honest force of gravity, a constant presence that anchors you to a world spinning through space at an unimaginable speed. Yet here, it feels like stillness. It feels like peace. This is the first layer of mediation. The world's furious motion is translated into a feeling of quiet stability. Notice the air. Feel it at the edge of your nostrils, a little cooler as you breathe in, a little warmer as you breathe out. That air has a history. It has been warmed by sunlight striking the far side of the planet, cooled by the vastness of the night sky above. It has tumbled over oceans, carrying the memory of water. It has brushed against the leaves of forests, carrying the scent of soil and life. It is a river of molecules connecting you to the entire globe, yet it arrives here, in this room, as a gentle, rhythmic, and personal current. It is the planetary breath, scaled down to the intimacy of your own. This, too, is a buffer. The chaotic, global circulation of the atmosphere becomes this simple, life-sustaining presence. Listen to the sounds of your environment. Perhaps there is a deep hum from an appliance, the distant rumble of a passing vehicle, or maybe just the profound quiet of a sleeping house. Each sound travels through the medium of the air, its vibrations dampened and softened by distance, by walls, by the very fabric of the room. The world is a place of constant, roaring energy, but what reaches you here is a curated soundscape, a muffled and gentle version of reality. Your ears are protected from the full acoustic power of the planet by the simple physics of insulation and distance. And what of the light? Perhaps the room is dark, but for a sliver of moonlight under a door, or the faint glow of a digital clock. This darkness is not an absence of light, but a presence of shadow. You are resting in the shadow of the Earth itself, a vast planetary shield that has turned you away from the sun's brilliant gaze. The transition from day to night is perhaps the most fundamental buffer we experience, a rhythm so profound that it has shaped the biology of every complex creature on this planet. It is a daily promise of respite, of coolness, of a time for repair and integration. Without this simple rotation, this turning away, life as we know it would be impossible. So, here you are, anchored by gravity, breathing the filtered air, resting in the quiet, held in the planetary shadow. Before we even begin to speak of grander systems, notice how your immediate sensory world is already a place of profound mediation. You are not experiencing the raw, unfiltered universe. You are experiencing a carefully modulated, buffered, and stabilized version of it. You are living in an intricately constructed sanctuary, and it is from this place of safety, this place of immediate and tangible peace, that our journey truly begins. We start not with an abstract idea, but with the felt reality of this very moment. You might wonder why we would spend our time on such a grand and seemingly abstract question: what are the stakes of imagining life on the Sun? The answer, like the systems we will explore, exists on multiple timescales at once. On the human scale, the timescale of your own life, the stakes are about perspective. In our daily lives, we are often caught in cycles of urgency, of immediate problems demanding immediate solutions. We experience the world as a series of sharp edges of causes and direct effects. This mindset is necessary for navigating our complex human world, but it can also be exhausting. It can make us feel isolated and responsible for controlling forces that are far beyond our influence. By stepping back, by zooming out to the planetary scale, we are not abandoning our responsibility, but contextualizing it. We begin to see that the world is not just a collection of sharp-edged problems, but also a network of deep, slow, and resilient systems. Understanding the atmospheric and geological buffers that stabilize our world can cultivate a sense of patience. It reminds us that change happens on many timelines, and that the planet has a wisdom and a resilience that operates on a scale far beyond our own anxieties. It offers a kind of quiet reassurance. We are part of something vast, ancient, and profoundly self-regulating. This perspective doesn't solve our immediate problems, but it can soften their edges. It can reduce the feeling of frantic urgency and replace it with a more grounded, long-term view. On the geologic timescale, the stakes are about understanding the very conditions that allow for our existence. Life on Earth has persisted for billions of years through periods of intense volcanism, asteroid impacts, and dramatic shifts in the Sun's own output. It has survived because the planet is not a passive rock in space. It is an active, dynamic system with powerful feedback mechanisms that tend to keep conditions within a habitable range. By exploring these mechanisms, these planetary shock absorbers, we are uncovering the deep logic of our own home. We are learning the rules of the game we are a part of. This understanding is not just academic. It helps us interpret the changes we see happening in our own time. It allows us to distinguish between a minor fluctuation and a fundamental shift in a planetary system. It gives us the language to describe the immense inertia of the climate system, the way a small change now can have consequences that unfold over centuries. It moves us from a place of simple reaction to a place of deeper comprehension. We start to see the world less like a machine that we can simply fix, and more like a living organism that we must learn to cooperate with. So, the stakes are both intimate and immense. It is about finding a calmer, more resilient way to inhabit our own lives, and it is about developing the wisdom to navigate our collective future on this planet. Our thought experiment of living on the Sun serves as the ultimate baseline, a world of no resilience, no buffers, no second chances. By holding that imagined world in our minds, the real-world systems of our planet come into sharper focus. Their importance becomes undeniable. Their quiet, persistent work becomes something we can not only understand but also feel a deep sense of gratitude for. It's a journey from the abstract to the personal, from the planetary to the peace you feel in this very room. As we move forward, we will begin to trace a few specific threads, a few lines of inquiry that will weave together throughout our exploration tonight. Think of these not as a list to be memorized, but as gentle signposts, promising a return to ideas that are rich and interconnected. We will touch upon them lightly now, and then revisit them in greater depth as our journey unfolds. The first thread is the idea of time as a buffer. We often think of time as a neutral, forward-marching arrow, but in the context of planetary systems, time is a crucial ingredient in the recipe for stability. A forest fire is a catastrophe in the moment, but over the course of a century, it is part of a cycle of renewal. The climate of the Earth can absorb a certain amount of change, but only if that change happens slowly enough for its feedback systems to respond. We will explore how the planet uses deep time, the slow grinding of tectonics, the gradual accumulation of sediments, the patient cycling of water, to smooth out the sharp shocks that would otherwise be catastrophic. What happens when changes occur faster than the system's ability to buffer them? We will return to this question of pace and timing. A second thread we will follow is the concept of life as an active participant, not a passive passenger. It is easy to imagine life as something that simply arose on a conveniently habitable planet. But the more we learn, the more we see that life itself has profoundly shaped the planet's habitability. The very oxygen in the air you are breathing is a product of ancient bacteria. The chalky cliffs of Dover are the collected shells of trillions of marine organisms, a massive store of carbon that helped regulate the global climate. We will investigate this quiet conversation between the living and the non-living, the way biomes and geology work together to create a resilient, self-sustaining world. Life is not just living on the Earth, it is actively co-creating the Earth it lives on. We will pick up this thread of biological agency again, and a third thread, perhaps the most subtle, is the distinction between a complicated system and a complex one. A complicated system, like a watch, has many parts, but they interact in predictable, linear ways. If one gear breaks, the watch stops. A complex system, like a rainforest or the global economy, also has many parts, but they interact in non-linear, unpredictable ways. It can absorb shocks and reroute functions. It can heal. It is resilient. Our planet is a complex system. Its stability does not come from perfect, rigid control, but from a flexible, adaptive dance of interconnected elements. We will explore what this means for our understanding of planetary health and how this idea of complexity over complication offers a more hopeful and realistic model for our future. So keep these ideas gently in mind: time as a buffer, life as a creator, and the resilience of complexity. We have now planted these seeds. There is no need to grasp them tightly. They will sprout and grow in their own time as we continue our descent into the quiet, interconnected wonder of our world. To ensure our journey is clear, let's establish a few working definitions. We'll use plain language, translating complex ideas into simpler, more intuitive forms. The goal here isn't to be overly technical, but to have a shared set of concepts that we can build upon as we go. First, let's define our central metaphor: living on the sun. As we've touched on, this does not mean literally inhabiting a star. For our purposes tonight, it means existing in a system with zero buffering capacity. It is a world of pure input and immediate output. If energy comes in, the temperature instantly rises. If a meteor strikes, the crater remains forever. There are no oceans to absorb heat, no atmosphere to burn up projectiles, no life to heal the scar. It is a world without forgiveness, without memory, without the capacity for healing or regulation. It is a baseline of pure physics, a hypothetical control group against which we can measure the complexity of our own world. Next, let's define what we mean by a buffer, or a meta-mediating system. A buffer is anything that slows down, absorbs or transforms an input, creating a delay between cause and effect. Think of the shock absorbers on a car. They don't eliminate the bumps in the road, but they spread the impact out over time, turning a sharp jolt into a gentle bounce. On Earth, the oceans are a massive thermal buffer. They can absorb vast amounts of heat energy from the sun with only a very gradual change in temperature. The atmosphere is a chemical buffer, absorbing and transforming gases. Soil is a hydrological buffer, holding rainwater and releasing it slowly to plants. These systems create stability by dampening shocks and smoothing out extremes. They introduce a crucial delay, a moment of pause that allows the wider system to adjust. Now, what is a feedback loop? This might sound technical, but the concept is simple and familiar. A feedback loop is a circular chain of cause and effect. There are two main types. The first is a reinforcing, or A positive, feedback loop. This is a vicious cycle where A causes more of B, which in turn causes more of A. Think of a microphone held too close to a speaker. The sound gets amplified, which gets picked up and amplified again, creating a loud screech. In climate, the melting of ice is a reinforcing feedback. White ice reflects sunlight. When it melts, it exposes dark ocean or land, which absorbs more sunlight, which causes more warming, which melts more ice. These loops accelerate change. The second, and for our story tonight, the more important type, is a balancing kitsuki negative feedback loop. This is a stabilizing cycle where A causes more of B, but more of B then causes less of A. The classic example is a thermostat. When the room gets too hot, A, the thermostat turns on the air conditioning. B, the air conditioning cools the room, reducing the heat, less of A, which then tells the thermostat to turn off the air conditioning. This loop keeps the temperature stable. Our planet is full of these balancing feedbacks. For instance, a warmer world evaporates more water, which creates more clouds. Some types of clouds reflect sunlight back into space, which can have a cooling effect. This is a planetary scale thermostat. Finally, we need to be clear about our assumptions. We are assuming that stability within a certain range is a precondition for the development and survival of complex life. We are also assuming that the Earth's systems can be understood as an interconnected whole, where the actions of the geology affect the oceans, which affect the atmosphere, which affects life, and which in turn affects the geology. This is the core idea of what is sometimes called Earth system science. With these simple definitions, the Sun as our unbuffered baseline, the Earth as a system of buffers, and feedback loops as the engine of regulation, we have the tools we need to begin our exploration in earnest. To appreciate the quiet machinery of our world, it helps to have a brief sense of where our understanding comes from. For most of human history, the Earth was seen as a passive stage upon which the drama of life, human and divine, unfolded. The mountains, oceans, and skies were a static backdrop, unchanging and eternal from our perspective. The ground beneath our feet was solid, reliable. The seasons followed a divinely ordained or simply mechanical rhythm. The idea that the Earth itself was a dynamic, evolving entity was not part of the common world view. This began to change in the 18th and 19th centuries with the birth of modern geology. Scientists like James Hutton looked at the slow erosion of mountains and the gradual layering of sediments and realized that the Earth had a history, a deep, ancient history written in stone. They saw that the forces shaping the world today, wind, water, ice, were the same forces that had been shaping it for millions, even billions of years. This was a profound shift. The Earth was no longer a static stage, but an active, changing character in its own story. The concept of deep time was born, a timescale so vast it dwarfs the entirety of human history. In the 20th century, the perspective shifted again. With the advent of technologies like sonar and seismology, we began to see that the solid ground was not so solid after all. The theory of plate tectonics revealed that the Earth's crust is broken into massive plates that are constantly in motion, floating on a sea of molten rock. This discovery explained everything from the location of volcanoes and earthquakes to the uncanny jigsaw puzzle fit of continents like Africa and South America. The Earth was not just old and changing, it was alive with motion, its very surface constantly being recycled and reborn. But the most recent and perhaps most profound shift in understanding came from looking back at our planet from the outside. The space race of the 1960s gave humanity its first view of the Earth from a distance, a beautiful, swirling blue marble suspended in the blackness of space. This image, often called the blue marble, had a powerful effect. For the first time, we could see the Earth's systems not as separate domains, ocean, land, air, but as a single, interconnected, and visibly finite whole. You could see the weather systems moving across continents, the dust from the Sahara fertilizing the Amazon rainforest. This holistic view gave rise to Earth system science. Scientists began to use satellites and supercomputers to model the planet as one integrated system. They confirmed that life wasn't just a passenger on this dynamic planet. It was a powerful geological force in its own right. They discovered the deep, interconnected feedback loops that link the living biosphere with the non-living geology and chemistry of the planet. It was this perspective that revealed the planetary-scale regulatory systems we will be exploring tonight. Our journey, then, is built upon this cumulative understanding, the discovery of deep time, the revelation of a dynamic surface, and the holistic vision of an interconnected living planet seen for the first time from the silence of space. Let's begin our exploration of the Earth's buffering systems at the scale we know best, the human scale. These are the patterns so deeply embedded in our daily lives that we often fail to see them as part of a planetary system. They are the first and most intimate layers of mediation between us and the raw energy of the sun. Consider the simple, profound act of seeking shade on a hot day. You move from the direct glare of the sun into the cool relief offered by a tree, a building, or even a passing cloud. In that moment, you are participating in a fundamental planetary process. The object casting the shadow is intercepting solar radiation, absorbing its energy and re-radiating it more gently as heat. You are taking refuge in a temporary, localized buffer. On our imagined sun world, there is no shade. Energy arrives everywhere, all at once with no interruption. There is no relief, no place to cool down. The very concept of shelter is a consequence of living on a solid, opaque planet. Now let's scale this up. The most significant shadow we experience is the one we are in right now, the shadow of the Earth itself. The daily cycle of day and night is the planet's primary thermal regulation strategy. For roughly half of every rotation, your location on Earth is turned away from the sun, plunging it into the cold of space. During this time, the land and water that absorbed heat all day radiate it back out. This nightly exhalation prevents a runaway buildup of heat. It is a planetary-scale reset, a deep, rhythmic breath. Life has evolved to dance to this rhythm. Plants have metabolic cycles tied to the sun's presence. Animals have patterns of activity and rest. Your own body has a circadian rhythm, a deep, internal clock synchronized to this daily turning. This fundamental pulse of light and dark, warmth and cool, is the heartbeat of the biosphere. What is the mechanism here? It is simply the Earth's rotation and its opacity. Because the planet is a solid sphere, only one half can be illuminated at a time. Because it spins, that illumination is distributed, passed around like a shared resource. Imagine if the Earth were tidally locked to the sun, with one side perpetually facing it and the other in perpetual darkness. The day side would be scorched into a lifeless desert, while the night side would be frozen solid. The boundary between them, a terminator zone, might hold a sliver of potential habitability, but it would be a world of extreme, permanent gradients. Our spin, our daily rotation, is a crucial mechanism for thermal balance. It smooths out the energy input, preventing the extremes that would arise on a static world. The implication of this is profound. It means that time itself, in the form of this daily cycle, is one of the first and most important buffers against the sun's overwhelming energy. The 24-hour day isn't just a convenient way to measure our lives, it's a fundamental condition for life's existence. It creates the alternating periods of energy surplus and energy deficit that drive everything from weather patterns to the metabolism of a single cell. On our hypothetical sun world, time is flat. There is no cycle, no rhythm, no day or night. It is a state of perpetual, unchanging high noon. So the next time you enjoy the cool of the evening or wake to the gentle light of dawn, you are experiencing the benefit of this grand mechanical dance. You are living within a system that uses rotation and shadow to create a livable rhythm. This simple pattern, this daily turning away, is the first and most profound no that the Earth says to the sun's constant, unfiltered yes. And this raises a question: what other, less obvious cycles and buffers are at play, operating on scales far beyond our daily perception? Now that we have established the daily rotation as a primary buffer, Let's explore some of its boundaries and implications. What happens when this simple system is pushed to its limits? What can we learn from the edge cases here on our own planet? Consider the Earth's poles. In the Arctic and Antarctic circles, the daily cycle of light and dark breaks down for part of the year. Due to the tilt of the Earth's axis, a topic we will return to in great detail, these regions experience periods of 24-hour daylight in the summer and 24-hour darkness in the winter. In these moments, they get a small taste of what a non-rotating or tidally locked world might feel like. The result is a world of extremes. The long summer day allows for a massive influx of solar energy, leading to a burst of life, with algae blooming and animal populations surging. But it is a frantic, short-lived boom. The long winter night is a period of profound energy deficit, where temperatures plummet and life goes dormant or migrates away. The ecosystems at the poles are exquisitely adapted to this boom and bust cycle, but they are also incredibly sensitive. The life that thrives there is specialized. You do not find the same diversity of life as you do in the tropics, where the day-night cycle is stable and predictable year-round. The poles demonstrate a key principle. The more stable and predictable the energy input, the more complex and diverse the life that can be supported. The extreme seasonality of the polar regions acts as a filter, allowing only the most resilient and specialized organisms to survive. This stress tests our claim about the importance of the daily cycle. Where the cycle is weakest, life is more precarious. Let's also consider elevation. If you climb a high mountain, you get closer to the raw, unfiltered power of the sun. The atmosphere above you is thinner, providing less of a shield. The sun's rays feel more intense. The difference between the temperature in the direct sun and the temperature in the shade is much more dramatic than at sea level. At night, with less atmospheric blanket to trap heat, temperatures can drop precipitously. High-altitude environments are, in a sense, a step closer to our sun world. They are less buffered, and again we see the consequences in the biosphere. Life must be tougher, more resilient. Trees become stunted, growing into gnarled forms to resist the wind and radiation. Animals have adaptations to deal with the intense UV light and extreme temperature swings. The richness and diversity of life decreases as the buffering effect of the atmosphere thins. These edge cases, the poles and the mountains, don't disprove the importance of our planetary buffers. On the contrary, they confirm it. They show us what happens when those buffers are thinned or temporarily removed. They reveal the stress that unfiltered energy places on living systems. They act as natural laboratories, demonstrating the value of mediation. The stability and lushness of a tropical rainforest are not an accident. They are a direct consequence of being in a location with a highly regular day-night cycle and a thick, moist atmospheric blanket. The system is most buffered there, and life responds with an explosion of complexity and diversity. The implication is that our planet is not uniformly habitable. It is a patchwork of environments with varying degrees of buffering. The places we find most comfortable and productive are the places where these mediating systems, the daily cycle, the thick atmosphere, the presence of water, are working most effectively. We instinctively seek out these buffered zones. We build our homes with roofs to create artificial shade and insulation to mimic the atmosphere's thermal regulation. Human civilization is, in many ways, an exercise in building additional layers of buffering on top of the ones the planet already provides. We are creatures that not only benefit from mediation, but actively create more of it. Having examined the most basic mechanical buffer, the Earth's rotation, let's now zoom out to a more dynamic and complex layer of mediation, the atmosphere. If the planet's spin is its primary on-off switch for solar energy, the atmosphere is the planet's thermostat and shield. It is a system of intricate feedbacks that actively regulates the surface temperature, keeping it within the narrow range suitable for liquid water and therefore life. The first and most obvious function of the atmosphere is as a selective filter. Sunlight is not a single, uniform type of energy. It is a spectrum of radiation, from high-energy ultraviolet (UV) rays to visible light to lower-energy infrared. Our atmosphere, specifically the ozone layer in the stratosphere, is incredibly effective at absorbing the most damaging UV radiation. Without this ozone shield, the sun's energy would be sterilizing, shattering the delicate molecular bonds that are the basis of life. This is a crucial, non-negotiable buffer. On our sun world, there is no atmosphere. All radiation, from the most benign to the most lethal, strikes the surface with its full, unfiltered intensity. But the atmosphere's role as a thermostat is even more subtle, involving a delicate dance of balancing feedback loops. The key players in this dance are what we call greenhouse gases, such as water vapor, carbon dioxide, and methane. These gases are transparent to the incoming visible light from the sun, allowing that energy to pass through and warm the Earth's surface. However, they are opaque to the outgoing infrared radiation, heat, that the Earth radiates back. They trap some of this outgoing heat, acting like a planetary blanket. Without this natural greenhouse effect, the average temperature of the Earth would be about -18 degrees Celsius, well below the freezing point of water. The entire planet would be a ball of ice. This is where the feedbacks come in. Let's trace a few of these stabilizing or negative feedback loops. As we mentioned earlier, if the Earth warms, more water evaporates from the oceans. This puts more water vapor, a powerful greenhouse gas, into the atmosphere, which could lead to more warming, a reinforcing feedback. However, more water vapor also leads to the formation of more clouds. Low, thick clouds are very bright and act like mirrors, reflecting incoming sunlight back into space. This has a cooling effect, counteracting the initial warming. This interplay between water vapor and clouds is one of the planet's primary thermostats. It is a self-regulating system that tends to resist being pushed too far in either direction. There is no intention here, no conscious design. It is simply the emergent consequence of the physics of water and air. Another crucial balancing feedback operates on a much longer geological timescale. This is the carbonate-silicate cycle. It works like this. Carbon dioxide in the atmosphere dissolves in rainwater, forming a weak carbonic acid. This acid rain falls on the land and chemically weathers silicate rocks. The weathering process releases calcium and bicarbonate ions, which are washed into the oceans by rivers. In the oceans, marine organisms like plankton and corals use these ions to build their shells and skeletons out of calcium carbonate. When these organisms die, their shells sink to the ocean floor, forming layers of limestone. This process effectively takes carbon dioxide out of the atmosphere and buries it in the rock record. Now here is the feedback part. The rate of chemical weathering is dependent on temperature. When the planet is warmer, there is more rain, and the chemical reactions happen faster, pulling more CO2 out of the atmosphere. This has a cooling effect, counteracting the initial warming. If the planet gets too cold, weathering slows down, less CO2 is removed, and the CO2 from volcanic eruptions gradually builds up in the atmosphere, warming the planet back up. This cycle acts as a planetary thermostat over millions of years. It has been a key factor in keeping the Earth's climate stable enough for life to persist, even as the sun itself has gradually grown brighter over billions of years. This is not teleological, it's a robust geochemical equilibrium. This system doesn't want to be stable, but its dynamics create stability. What if these regulatory systems didn't exist? Our sun world gives us the answer. Without an atmosphere, there is no greenhouse effect to keep the surface warm enough for liquid water and no ozone layer to protect against harmful radiation. But more importantly, there are no feedback loops. There is no thermostat. Any change in the sun's output, any major asteroid impact, would permanently alter the planet's state. There is no capacity for recovery. The existence of these complex atmospheric feedbacks on Earth implies a world that is not just habitable by chance, but is actively self-regulating. The existence of these feedback systems, particularly the balancing or negative feedbacks has profound second-order effects. The first is the creation of a relatively stable climate over geological time. This stability is not a flat line. The Earth's history is punctuated by ice ages and warm periods. But the fluctuations have, for the most part, remained within a range that allows life not just to survive, but to diversify and thrive. This persistence is remarkable. Think of it like a house with a very good but not perfect thermostat. The temperature might fluctuate by a few degrees, but it doesn't swing between boiling and freezing. This long-term stability has provided a reliable canvas upon which the slow, patient process of evolution can paint its masterpieces. Without it, life might never have progressed beyond the microbial stage, constantly being reset by climate catastrophes. A second implication is that the system has inertia. Because of the vast heat capacity of the oceans and the long timescales of cycles, like the carbonate-silicate weathering loop, the Earth's climate system responds slowly to change. It is like trying to turn a massive cargo ship. You can turn the rudder, but the ship will continue in its original direction for a long time before it begins to change course. This inertia is a double-edged sword. It is a powerful buffer against rapid natural fluctuations. A massive volcanic eruption can temporarily cool the planet, but the system's inertia will ensure it eventually returns to its equilibrium. However, this same inertia means that if the system is pushed by a new persistent forcing, such as a rapid, massive injection of greenhouse gases from an industrial civilization, the full effects will not be felt immediately. The warming we experience today is a response to emissions from decades past. The warming that future generations will experience is already baked in by our activities today. The system's slowness, its buffering capacity, creates a dangerous lag between our actions and their consequences. This leads to the concept of tipping points. A complex system with feedback loops is not always linear. You can push it, and it might seem to respond only gradually. But if you push it past a certain threshold, a reinforcing, positive feedback loop can take over, leading to a rapid, non-linear, and often irreversible shift to a new state. We saw this with the ice albedo feedback. Melting ice absorbs more heat, which melts more ice. If enough ice melts, this process can become self-sustaining, tipping the climate into a much warmer, hothouse state. The stability provided by balancing feedbacks is not infinite. The system is resilient but not invulnerable. Its sensitivity is not a sign of weakness, but a characteristic of its complexity. The very mechanisms that keep it stable can, under certain conditions, become engines of dramatic change. Finally, the interconnectedness of these systems means that a change in one place can have unexpected consequences elsewhere. The dust from the Sahara fertilizing the Amazon, which we mentioned earlier, is a perfect example. The health of the world's largest rainforest is dependent on the climate of the world's largest desert, thousands of miles away. These teleconnections make the Earth system behave in ways that are often counterintuitive. We cannot simply isolate one part of the system and expect to understand it. Everything is coupled. The implication for us is one of humility. We are living within a system whose complexity we are only just beginning to grasp. It is robust, but its stability is contingent on a delicate balance of forces and feedbacks that have been honed over billions of years. This isn't a call for alarm, but for a deep and abiding respect for the intricate machinery that makes our world work. As we continue this journey together, pausing here and there to look more closely at the world around us, it's a nice moment to simply acknowledge our shared presence in this exploration. Perhaps you are listening to this in the deep of night, with your city or town settled into a profound quiet. Or maybe you are on the other side of the world, where the sun is just beginning to rise, painting the sky in soft colors. Wherever you are, whatever time it is, you are part of a community of listeners, all resting, all allowing curiosity to guide them toward a place of calm. There is something comforting in that shared experience, a quiet solidarity in this act of gentle learning. If you feel so inclined, you might take a moment to notice one small detail in your room that speaks to the themes we are exploring. The way a curtain buffers the faint light from outside, the way a blanket traps your body heat, creating a stable microclimate. These small domestic comforts are tiny echoes of the grand planetary systems we are discussing. And if this journey is proving restful for you, if it is helping to quiet your mind, we would be grateful if you would consider liking, subscribing, or sharing this with someone else who might find some peace in it. There is no pressure to do so. Our primary hope is simply that this time together serves you well. Now let's settle back in, let your breath be easy, and let us return to the vast, quiet workings of our planetary home. Now, in the spirit of fair and thorough inquiry, it is crucial that we pause and consider the strongest counter-arguments to the picture we have been painting. We have been describing the Earth as a complex, self-regulating system, almost like a single organism. The mainstream or conventional scientific explanation, while acknowledging all the individual processes we've discussed, would frame them differently. It would caution against language that implies purpose or a holistic, lifelike quality to the planet. This more conventional view, let's call it the geophysical model, would argue that the Earth is, first and foremost, a physical object governed by the laws of physics and chemistry. It is an exceptionally lucky planet, but not a sentient or goal-directed one. From this perspective, the Earth's habitability is a product of a series of fortunate coincidences. It happens to be in the right orbit around the right kind of star. It happens to have the right mass to hold on to an atmosphere and a molten core to generate a protective magnetic field. It happens to have a large moon to stabilize its axis. Each of these is a roll of the cosmic dice, and Earth just happened to win the lottery. In this model, the feedback loops we've described are not part of a coordinated system designed to maintain stability. They are simply individual, disconnected geochemical and physical processes. The carbonate-silicate cycle, for example, is not a planetary thermostat. It is a chemical reaction whose rate is sensitive to temperature. The fact that it has a stabilizing effect on the climate is a fortunate side effect, not its purpose. The system has no purpose. It just is. Life, in this view, is a tenacious opportunist that arose in this lucky environment and has been adapting to the planet's changes ever since. Life is a passenger, albeit a very influential one that has significantly altered the chemistry of the atmosphere and oceans, but it is not the driver of the bus. This viewpoint would also stress the periods in Earth's history when regulation has failed dramatically. The snowball Earth events, for example, where the entire planet may have frozen over for millions of years, are evidence that the thermostat can break. The great extinction events, like the one that wiped out the dinosaurs, show that the system is vulnerable to catastrophic shocks. These are not signs of a resilient self-regulating system, but of a chaotic and often violent one, where stability is the exception rather than the rule. Furthermore, this perspective would be deeply skeptical of any language that sounds teleological, that is, language that suggests a goal or purpose. To say the Earth maintains a habitable climate is, to a strict geophysicist, a misleading personification. The Earth does not do anything. Processes occur. These processes have consequences. Some of those consequences have, by chance, been beneficial for life. It's a subtle but important distinction. It replaces the image of a complex, integrated system with the image of a vast, contingent, and ultimately random machine. This is the Steelman argument. It is strong because it is grounded in a rigorous reductionist approach that has been incredibly successful in science. It avoids making claims that cannot be directly tested and sticks to the observable mechanics. It explains all the same phenomena we have discussed, the carbon cycle, cloud formation, ice albedo feedback, without needing to invoke a higher-level concept of a single, integrated Earth system. It is a world of incredible luck, not of emergent design. And for many scientists, this is a more honest and less speculative account of our planet. Alongside the mainstream geophysical model, there are other interpretations that exist in the space between a purely random system and a purposefully designed one. These alternative models don't necessarily contradict the known facts of geology and physics, but they assemble those facts into a different and sometimes more provocative picture. One of the most famous alternative interpretations is the Gaia hypothesis, first proposed by scientist James Lovelock and microbiologist Lynn Margulis in the 1970s. The core idea of Gaia is that the Earth's living organisms, the biosphere, and its non-living components, the atmosphere, oceans, and rocks, are tightly coupled as a single, self-regulating complex system. This system, which they named Gaia after the Greek goddess of the earth, actively maintains the conditions for life on the planet. This goes a step beyond just saying that life influences the planet. The Gaia hypothesis suggests that the sum of all life, through its collective metabolic and reproductive processes, creates and maintains the very conditions of its own survival. In this view, the stability of the Earth's temperature, the chemical composition of its atmosphere, and the salinity of its oceans are not happy accidents of geology. They are emergent properties of a 4-billion-year-old evolutionary process in which life and its environment have co-evolved as one. Lovelock and Margulis pointed to several key anomalies to support their case. For example, the Earth's atmosphere is in a state of extreme chemical disequilibrium. It is rich in oxygen, a highly reactive gas, and also contains methane. In the presence of sunlight, oxygen and methane should quickly react and disappear. The fact that they coexist in stable concentrations means that something, namely life, is constantly pumping them into the atmosphere at a massive rate. The atmosphere, from this perspective, is not just a geological feature. It is a construction, like a bird's nest or a beehive, built and maintained by the planet's biosphere. Now there are weak and strong versions of this idea. The weak Gaia version, which is now largely accepted and forms the basis of Earth system science, is that life is a powerful force that influences planetary systems. The strong Gaia version, which is more controversial, suggests that the system behaves as if it were a single, goal-directed organism, with the goal being the preservation of life. This does not imply consciousness or intent, but rather that the emergent behavior of the whole system acts to regulate itself. Another alternative interpretation focuses on the principles of complexity theory. This view would suggest that any sufficiently complex system with a constant flow of energy, like a planet with a star, will tend to self-organize. The ordered structures we see, from weather patterns to ecosystems to the global climate, are not a result of luck or of life's intention, but are a natural consequence of the laws of thermodynamics operating in a complex, open system. Stability and regulation are not a miracle, they are a predictable outcome of complexity itself. The system learns and remembers by embedding information in its structures, whether in the DNA of an organism or the layers of sedimentary rock. These alternative views, Gaia and complexity theory, offer a different kind of narrative. They place less emphasis on randomness and coincidence and more on connection, coevolution, and emergence. They see the Earth not as a lucky rock, but as a system that has, over billions of years, developed a deep, inherent resilience. They present the facts side by side with the geophysical model, not to declare one right and the other wrong, but to show that the same set of evidence can be interpreted through different lenses, each revealing a different facet of the same deeply mysterious truth about our home. It is one thing to talk about these vast systems, and another to understand how we know what we know. Our knowledge of the Earth's deep past and its intricate workings is not direct. We cannot put the planet in a laboratory. Instead, we are like detectives arriving at the scene of a crime that happened millions of years ago with most of the evidence washed away. What we know through ingenious and indirect methods, and it's crucial to acknowledge the limits of these methods. Our primary witnesses are what we call proxies. A proxy is an indirect measure of something we cannot measure directly. For example, we cannot go back in time and measure the temperature of the Earth 100 million years ago, but we can drill deep into the Antarctic ice sheet and pull up ice cores. These cores contain tiny bubbles of ancient atmosphere trapped when the snow fell. We can analyze the composition of that air to find out the concentration of carbon dioxide and other greenhouse gases. We can also measure the ratios of different isotopes of oxygen and hydrogen in the ice itself, which tells us the temperature at which the snow formed. The ice core is a proxy. It is a physical archive that holds a memory of past climates. Similarly, we can analyze the fossils of tiny marine organisms called foraminifera, found in sediment cores from the deep ocean floor. The chemical composition of their shells depends on the temperature of the water they grew in. By analyzing these shells layer by layer through the sediment, we can reconstruct a history of ocean temperatures stretching back tens of millions of years. Tree rings, layers of sediment in lakes, and the chemical makeup of ancient rocks all serve as similar proxies. They are the planet's natural archivists. But here is the inherent bias: these records are incomplete. Geological processes are constantly destroying the evidence. Tectonic plates get subducted and melted back into the mantle, taking their rock records with them. Erosion wears down mountains. The further back in time we go, the patchier and more fragmented the record becomes. Our knowledge of the last few million years is quite detailed. Our knowledge of the Earth a billion years ago is incredibly fuzzy, based on just a few scraps of surviving rock. We are reading a book with most of its pages missing. This leads to a profound methodological challenge known as survivorship bias. We are studying a planet that succeeded. We are living on an N of 1, a single data point. We know that Earth has maintained a habitable climate for nearly 4 billion years because if it hadn't, we wouldn't be here to study it. This is the anthropic principle. It's possible that for every Earth, there are 1,000 similar planets that failed, planets that fell into a runaway greenhouse effect like Venus, or lost their atmosphere and froze like Mars. We can't see those failures, we only see the one successful experiment, which can lead us to overestimate the odds of success. We might be tempted to see the Earth's stability as a deterministic outcome when it might have been an extraordinary stroke of luck. So, how we know what we know is through a process of painstaking, creative, and indirect detective work. We use the laws of physics and chemistry as we understand them today to interpret the faint signals left behind in the planet's archives. We build computer models to simulate how these systems might work, and we test those models against the proxy data. But we must always hold this knowledge with a degree of humility. We are limited by the evidence that has survived, and we are biased by the fact that we can only study a successful case. Our understanding is a provisional map, constantly being updated as we find new proxies and develop new tools. And with that humility in mind, we can now reopen our main thread, returning to the grand systems of the planet, holding this awareness of our own limited perspective. As we continue our exploration, let's pause for a moment to consider the very words we are using. The language we choose to describe complex systems is not neutral. It shapes our understanding and our emotional response. When we talk about the Earth, it is very easy to fall into the trap of using anthropomorphic language, that is, assigning human-like qualities, intentions, or actions to non-human entities. For example, we might say that the Earth breathes, that the rainforest acts as the lungs of the planet, or that the climate system tries to maintain stability. These are powerful and intuitive metaphors. They help us connect with these vast, abstract systems on a more personal level. The image of a breathing planet is beautiful and evokes a sense of a living, unified organism. There is a poetic truth to it. However, it is crucial to remember that these are metaphors, and like all metaphors, they have their limits. The Earth does not literally breathe. The exchange of gases between the atmosphere and the biosphere is a result of two opposing chemical processes: photosynthesis, which consumes carbon dioxide and releases oxygen, and respiration, which does the opposite. The net effect is a massive flux of gases, but it is not driven by a central, coordinated intelligence or a need to inhale and exhale. It is the emergent result of trillions of individual organisms all pursuing their own metabolic imperatives. The system looks like it's breathing, but the mechanism is distributed, not centralized. Similarly, when we say the system tries or wants to be stable, we are imposing a human concept of purpose onto a process that is driven by the blind logic of feedback loops. A thermostat does not want to keep the room at 70 degrees. It is simply a mechanical or electronic device where a rise in temperature triggers a switch that activates a cooling unit, which then lowers the temperature, which triggers the switch to turn off. The stability is an outcome of the system's structure, not its desire. The carbonate-silicate cycle does not care about keeping the planet habitable for us. It is a set of geochemical reactions whose rates happen to be sensitive to temperature in a way that creates a balancing feedback. The stability is a gift of the system's physics, not a sign of its benevolence. Why does this distinction matter? Because when our metaphors become too literal, they can lead to a misunderstanding of how these systems work. If we think of the Earth as a consciously self-healing organism, we might become complacent, assuming that Mother Nature will simply clean up our messes. But the system's resilience is not infinite, and its feedbacks are not designed for our benefit. They are simply consequences of physics and chemistry. If we push the system too far, it won't try to return to the state we prefer. It will simply settle into a new, stable state, one that might be much hotter and hostile to human civilization. The new state will be just as natural as the old one. The planet will be fine. It is our own place within its systems that is precarious. So, as we move forward, let's continue to use these powerful metaphors when they are helpful, but let's do so with a conscious awareness of their limits. Let's replace anthropomorphic verbs like tries and wants with more neutral, mechanistic language like tends to or results in. We can speak of the planet's systems as being self-regulating without implying they are self-aware. This linguistic discipline doesn't need to make our exploration colder or more distant. In fact, it can lead to a deeper and more profound sense of awe. The wonder is not that some intelligence is taking care of us. The wonder is that a stable, life-giving world can emerge from the blind, unguided dance of matter and energy, woven together through a web of intricate feedback over billions of years. To make these ideas more concrete, let's walk through a simple case study, applying the principles from our first evidence track, the patterns at the human scale. We'll use a second-person narrative to place you directly in the scene. Imagine you are standing in a vast, dry, open plain at midday. The sun is directly overhead. There is no wind, there are no clouds. This is a simplified environment, a little closer to our sun-world baseline. The input is clear and direct, intense solar radiation. The first thing you notice is the heat. The ground beneath your feet absorbs the sunlight, and its temperature rises steadily. It re-radiates that energy as long-wave infrared radiation, which you feel as a shimmering heat rising from the earth. The air just above the ground becomes superheated. You feel this intense energy on your skin, and your body immediately responds. Your sweat glands open, releasing moisture onto your skin. As this moisture evaporates, it carries away heat, a clever biological cooling system. This is your body's first line of defense, its own personal buffering system. But it comes at a cost. You are losing water. You look for shade. There is none. The solar input is uniform and relentless. Without a buffer, the environment is becoming hostile to you, a complex biological machine that can only operate within a very narrow temperature range. Your internal systems are working hard to maintain homeostasis, but they are fighting a losing battle against a massive, constant energy source. Now let's introduce a single, simple buffer, a large, solitary tree. You walk over and stand in its shadow. The change is immediate and profound. The direct, short-wave radiation from the sun is blocked. You are no longer the direct recipient of that energy. The leaves of the tree are absorbing it, using a fraction of it for photosynthesis and re-radiating the rest. The ground in the shade is significantly cooler than the ground in the sun, because it has been protected for hours. The air in the shade is cooler. Your body can relax. Your sweating slows. You have moved from a state of high stress to a state of relative equilibrium simply by placing an object between you and the energy source. But the tree is doing more than just casting a shadow. It is an active participant in creating this microclimate. Its roots draw water from deep in the soil, water that fell as rain weeks or months ago, a stored buffer. This water is pulled up through the trunk and out to the leaves, where it is released into the air through a process called transpiration. This is essentially plant sweat. This process has the same cooling effect as your own sweat, not just for the tree, but for the air around it. The shade of a living tree is cooler than the shade of a rock or a building of the same size because it is an active, evaporative cooler. Let's trace the chain of causality. The sun provides energy. The tree intercepts this energy, shade buffer. The ground stores water from past rains, time buffer. The tree accesses this stored water and releases it, evaporative buffer. The result is a small, local pocket of stability and coolness in an otherwise harsh environment. Now imagine this, not as one tree, but as a billion trees, a forest. The forest creates its own climate, a vast, buffered zone of shade, humidity, and stable temperatures. It is a system that has emerged from the simple interaction of sunlight, water, and life. You, in this scenario, did not have to understand the physics of radiation or the biology of transpiration. You simply had to follow a deep, evolved instinct. Seek shade. Your behavior is part of the feedback loop. By seeking the buffered environment, you increase your chances of survival. This simple case demonstrates the core principle we are exploring. Stability and life are found where energy is mediated, slowed down, and buffered. The journey from the sun-baked plain to the shade of the tree is a journey from our harsh sun world metaphor to the buffered, life-sustaining reality of our own. Now let's apply the same method to a contrasting scale, using the lens of our second evidence track, systems and feedbacks. We'll shift from the micro scale of a single person and a tree to the macro scale of the entire planet, and we'll look at one of the most critical transitions in Earth's history. Let's go back in time about 2.5 billion years to the Archean Eon. Imagine the Earth from space. The continents are small, volcanic islands. The oceans are not blue, but a murky, iron-rich green, and the sky is not blue, but a hazy orange. The atmosphere is composed mainly of nitrogen, carbon dioxide, and methane. There is almost no free oxygen. This was a world without the atmospheric system we know today. On this world, a new form of life had recently evolved, cyanobacteria. These single-celled organisms had developed a revolutionary new trick for capturing the sun's energy: oxygenic photosynthesis. They took in sunlight, water, and carbon dioxide, and as a waste product, they released a highly reactive, toxic gas, oxygen. For hundreds of millions of years, this oxygen did not build up in the atmosphere. The planet had a massive chemical buffer in place. The oceans were filled with dissolved iron, and as the cyanobacteria produced oxygen, it immediately reacted with this iron, causing it to rust out of the water and fall to the ocean floor. We can see the evidence of this today in massive geological formations called banded iron formations, which are a major source of our iron ore. The planet was absorbing this new, potent chemical, buffering the system against radical change. But no buffer is infinite. After millions of years of continuous oxygen production, the dissolved iron in the oceans was finally used up. The buffer was full. Now the oxygen began to escape into the atmosphere. This triggered what is known as the Great Oxidation Event, arguably the most significant pollution event in the planet's history. This is where the feedbacks kick in. Oxygen is a powerful greenhouse gas destroyer. It reacted with the methane in the atmosphere, which was a key gas keeping the planet warm at a time when the sun was significantly dimmer than it is today. As atmospheric methane levels plummeted, the planet's greenhouse blanket was thinned dramatically. The global thermostat was broken. This triggered a reinforcing feedback loop. A cooler planet allowed ice sheets to grow. The white ice reflected more sunlight back into space, the ice albedo effect, which cooled the planet further, which allowed the ice to expand even more. The result was the first and most severe snowball Earth event, a global deep freeze that lasted for millions of years. The system, pushed past its buffering capacity, tipped into a new, stable, but hostile state. This event demonstrates the power and danger of systems-level change. The cyanobacteria were not intending to change the world. They were just living, metabolizing and reproducing. But their collective action, scaled up over millions of years, overwhelmed a planetary buffer and triggered a series of catastrophic feedbacks. It shows that even a biological innovation can have profound, planet-altering geological consequences. But the story doesn't end there. Over millions of years, another, much slower process continued. Volcanism. Volcanoes continued to pump carbon dioxide into the atmosphere. With the planet covered in ice, the normal process of CO2 removal, the weathering of rocks, had ground to a halt. So CO2 levels in the atmosphere began to rise very, very slowly. After millions of years, the greenhouse effect from this CO2 became strong enough to start melting the ice. Once the melting started, the ice albedo feedback kicked in, but this time in reverse. Dark ocean water absorbed more heat, which melted more ice, and the planet rapidly, violently, swung out of its snowball state into a hothouse state. This entire saga, from the first breath of oxygen to the snowball and back, illustrates the principles of Track 2 on a grand scale. We see a system held stable by a chemical buffer, dissolved iron. We see that buffer get overwhelmed. We see the system tip into a new state, driven by a reinforcing feedback loop, ice albedo, and we see it eventually rescued by a very slow, long-term balancing feedback, volcanic CO2 buildup. It's a powerful reminder that our planet's stability is not a given. It is a dynamic balance of powerful forces, and the transitions between states can be dramatic and world-altering. Let's now widen our view even further to the scale of celestial mechanics. So far, we have focused on buffers and systems originating on the Earth itself. But one of the most crucial elements for Earth's long-term climate stability is not on our planet, but orbits around it, the Moon. The Earth-Moon system is a coupled pair, a gravitational dance that has had profound consequences for the habitability of our world. The most important effect of our large moon is the stabilization of Earth's axial tilt, also known as its obliquity. The Earth is not spinning perfectly upright relative to its orbit around the Sun. It is tilted on its axis by about 23.5 degrees. This tilt is the reason we have seasons. When the northern hemisphere is tilted toward the Sun, it receives more direct sunlight and experiences summer, while the southern hemisphere experiences winter, and vice versa. This regular, predictable cycle of seasons is a fundamental rhythm of life outside the tropics. Now here's the crucial part. The axial tilt of a planet is not inherently stable. Other planets in our solar system, like Mars, which has only 2 tiny moons, experience wild swings in their axial tilt over millions of years. Mars's obliquity is thought to have varied from nearly 0 degrees, no seasons, to over 60 degrees, incredibly extreme seasons. Such chaotic shifts would be devastating for a planet with complex life. Imagine a world where, over the course of a few 100,000 years, the tropics become the poles and the poles become the tropics. The climate would be in a constant state of violent upheaval. It would be nearly impossible for stable, long-term ecosystems to establish themselves. Earth has been spared this chaotic fate because of the gravitational pull of our unusually large moon. The moon acts like a massive gravitational anchor, a stabilizing hand that prevents the Earth's axial tilt from wobbling chaotically. It keeps the tilt confined to a very narrow range, fluctuating only by a degree or two over tens of thousands of years. This gravitational coupling damps out the chaotic tendencies that would otherwise arise from the gravitational tugs of Jupiter and the other giant planets. The Moon is a planetary scale buffer against celestial chaos. There is another, more subtle effect of this coupling: tidal friction. The Moon's gravity pulls on the Earth, creating the ocean tides, but it also pulls on the solid body of the Earth itself, creating a slight bulge. As the Earth spins faster than the Moon orbits, this bulge is always slightly ahead of the Moon. The Moon's gravity then pulls back on this bulge, creating a frictional drag. This tidal friction has two main consequences. First, it is very slowly slowing down the Earth's rotation. When the Moon first formed, a day on Earth was likely only about 6 hours long. Over billions of years, tidal friction has slowed us down to the current 24-hour day. Second, by the law of conservation of angular momentum, as the Earth's spin slows, the Moon is slowly pushed into a higher orbit. It is currently moving away from us at a rate of about 3.8 centimeters per year, about the speed your fingernails grow. This might seem insignificant, but over geological time, it is a major change. This whole process, the stabilization of our axis and the gradual lengthening of our day, is an example of a macro-scale coupling that has created a more stable and predictable environment. On our Sun World thought experiment, we imagine a world of pure, unmediated energy. But here we see that even our relationship with the cosmos is mediated. We are not just a solitary planet, we are part of a dynamic system. The Moon's steadying presence has provided the long-term climatic stability that has allowed the slow, patient process of evolution to unfold without being constantly reset by orbital chaos. It is a quiet, gravitational gift that has made all the difference. The implications of this planet-moon coupling are profound, translating directly from celestial mechanics into the lived experience of time and the conditions for life. The long-term stability of Earth's axial tilt, courtesy of the Moon, is arguably a key ingredient for planetary habitability. First, it creates predictable and reliable seasons. This predictability is the foundation upon which complex ecosystems are built. Plants have evolved to time their germination, growth, and flowering to the seasons. Migratory animals use the changing length of the day as a cue to begin their epic journeys. Hibernating animals know when to prepare for the lean months of winter. This intricate choreography of life is only possible because the seasonal rhythm is a stable, repeating pattern over thousands, even millions of years. If the axial tilt were chaotic, as it is on Mars, the very concept of a reliable season would disappear. The rules of the climate would constantly be changing, preventing the development of these deep, co-evolved relationships between organisms and their environment. Evolution would be a constant scramble to adapt to a new normal, with little opportunity for the kind of specialization and complexity we see on Earth. Second, the stabilization of the tilt prevents climatic extremes. A planet with a very high axial tilt would experience unimaginably harsh seasons. The poles would point almost directly at the sun during their respective summers, leading to extreme melting and heat, while the winters would be plunged into a darkness and cold far more severe than what we experience. A planet with no tilt would have no seasons at all, which might sound pleasant, but would lead to a world with a permanently superheated equator and permanently frozen poles, creating a much stronger and more violent atmospheric circulation as the planet tried to balance these temperature extremes. The Moon's influence has kept us in a Goldilocks zone of axial tilt, not too much, not too little, creating a world with a wide range of habitable zones. The gradual slowing of the Earth's rotation driven by tidal friction also has significant consequences. A much faster rotation would lead to a very different world. The Coriolis effect, which drives the rotation of weather systems, would be much stronger. This would result in more numerous, smaller, and likely more violent storms. The atmosphere would be organized into many more distinct bands of circulation, creating a more striped appearance like Jupiter, with sharper and more extreme climate zones. The very shape of the continents and ocean basins would be different, as a faster spin would create a more pronounced equatorial bulge. By slowing the Earth down, the Moon has contributed to a calmer, less chaotic atmosphere. In essence, the Earth-Moon system translates the abstract principles of gravity and angular momentum into the tangible realities of lived time. It gives us a day long enough for significant cooling at night. It gives us seasons that are regular enough to plan a harvest or time a migration. It gives us a climate that is stable enough over geological time for evolution to build complex, resilient ecosystems. When we look up at the Moon in the night sky, we are not just seeing a beautiful, inert satellite. We are seeing a partner in a gravitational dance, a cosmic anchor that has buffered our world from chaos and helped to create the long, quiet, stable stretches of time necessary for a planet to become a home. To understand the Earth's history of regulation and change, we must learn to read its archives. The planet, as we've noted, has a memory. This memory is not stored in a brain, but in the physical and chemical layers of its own substance. Geologists and paleoclimatologists are the librarians of this archive, learning to decode the stories written in ice, rock, and mud. This is our fourth track of evidence, the deep time memory of the Earth. Let's return to the ice cores of Antarctica and Greenland. As snow falls each year, it compacts the layers below it, eventually forming ice. Each layer is a snapshot of the year it fell. By drilling down, sometimes for miles, scientists can pull up a continuous record stretching back hundreds of thousands of years. As we've discussed, bubbles in the ice trap ancient air, giving us a direct sample of past atmospheres. But the story is even richer than that. The ice also traps layers of volcanic ash, which can be dated to pinpoint major eruptions in the past. It traps dust blown from distant deserts, telling us about past wind patterns and aridity. It traps pollen from long-gone forests, allowing us to reconstruct ancient ecosystems. An ice core is a high-fidelity, year-by-year almanac of the recent planetary past. For a longer but less detailed view, we turn to the ocean floor. Rivers carry eroded sediment from the continents into the sea. This sediment, along with the shells of marine organisms and particles of dust from the air, settles in a constant, slow rain onto the deep ocean bottom. Over millions of years, this accumulation builds up thick layers. By drilling cores of this sediment, scientists can read a history that goes back much further than the ice cores, over 100 million years. The chemistry of the fossil shells tells us about temperature. The type of sediment tells us about erosion and continental climate. The fossils themselves tell us which organisms were living and which were dying at any given time. These deep-sea cores are the grand narrative history books of the planet. For the truly ancient history, billions of years ago, we must read the rocks themselves. The type of rock tells us about the environment in which it formed. Sandstone from a desert, shale from a muddy seabed, lava from a volcano. The orientation of magnetic minerals in the rock tells us the latitude at which the rock formed, allowing us to reconstruct the slow dance of the continents. The radioactive isotopes within the rock act as a clock, allowing us to date these ancient events with remarkable precision. The rock record is the most fragmented and difficult to read of all the archives, a book with most pages torn out and the remaining ones jumbled. Yet, it is the only record we have of the Earth's first few billion years. What do all these archives tell us? They tell a story of both stability and dramatic change. They show us that the major parameters of the planet, its temperature, the composition of its atmosphere, the positions of its continents, have always been in flux. But they also show us the power of the planet's regulatory systems. The archives record catastrophic events like massive asteroid impacts or periods of continent-spanning volcanism, and they show us how the Earth system responded and, eventually, recovered. They allow us to see the feedback loops in action. We can see CO2 levels rise, followed by a rise in temperature. We can see the advance and retreat of ice sheets in lockstep, with subtle, predictable wobbles in the Earth's orbit, known as Milankovitch cycles. These archives act as lagging indicators. They don't tell us what is happening now, but they give us a rich context for understanding the present. They provide the baseline against which we can measure the changes of our own era. By reading these memories stored in the Earth's own body, we learn the grammar and syntax of our planet. We see the patterns of its behavior, its sensitivities, and its profound resilience. We are learning to listen to the story the planet is telling about itself. While these natural archives provide an invaluable window into the past, it is crucial to understand their limitations. The signals they contain are often noisy, and our ability to interpret them is constrained. This leads us to the implications of relying on such evidence. What can we and what can't we confidently infer from these planetary memories? First, we can infer broad patterns and correlations with a high degree of confidence. For example, the ice core data shows an incredibly tight coupling between atmospheric carbon dioxide concentrations and global temperature over the last 800,000 years. The two lines on the graph rise and fall in near-perfect synchrony. This does not by itself prove that CO2 causes warming, but when combined with our understanding of physics, it provides powerful evidence for that relationship. We can confidently say that in the Earth's recent past, warmer periods have been associated with higher levels of greenhouse gases. We can also identify the timing of major events and shifts in the Earth system. We can pinpoint the Cretaceous-Paleogene extinction event that killed the dinosaurs to 66 million years ago with great precision because the geological signature, a thin layer of iridium-rich clay, the fallout from a massive asteroid impact, is found all over the world in rocks of exactly that age. We can see the relatively abrupt end of the last ice age around 11,700 years ago. These archives give us a timeline for the planet's history. However, the archives are much less clear about the rate of change in the past. An ice core might give us a resolution of a few years, but a deep-sea sediment core might average 1,000 years of history into a single centimeter of mud. This smoothing effect of the geological record makes it very difficult to detect changes that happened rapidly in the past. A change that feels instantaneous to us unfolding over a century might be completely invisible in a record that has a 1,000-year resolution. This is a critical limitation. When we look at the great climate shifts of the past, they often appear gradual in the rock record, but that could be an artifact of the blurry lens we are looking through. It's possible that past tipping points were crossed with a speed that felt just as alarming to the organisms of the time as our current changes feel to us. Another major constraint is that correlation does not equal causation. The archives can show us that two things happened at the same time, but they can't always tell us which one caused the other, or if both were caused by a third, unobserved factor. Unraveling these causal chains requires building complex models and testing them against the data, a process that is always fraught with uncertainty. There are still major debates among scientists about the precise sequence of events that led to the end of the ice ages, for example. Was it the orbital cycles, the rise in CO2, changes in ocean circulation, or some complex combination of all three? The archives provide the clues, but they don't solve the mystery for us. This means we must speak in terms of confidence bands. For some conclusions, like the fact that the Earth was much warmer during the age of the dinosaurs and had no polar ice caps, our confidence is very high. For others, like the exact temperature of the planet 3 billion years ago, our confidence is very low, and we must speak in terms of broad ranges and possibilities. This uncertainty is not a weakness of the science. It is an honest reflection of the difficulty of the task. It reminds us to be humble in our claims and to distinguish between what is well established, what is a reasonable inference, and what is pure speculation. The archives tell us a story, but it is a story we are still learning to read, full of smudged ink and missing pages. As we continue to weave together these different strands of evidence, from the microscopic life to the celestial dance, we are beginning to assemble a more holistic picture of our planetary home. We've looked at the buffers of time and space, the regulatory power of the atmosphere, the stabilizing presence of the moon, and the deep memories stored in the Earth's archives. Soon we will bring these threads together. We will attempt to synthesize them into a coherent model that moves beyond seeing them as separate processes. We will explore how these different systems are not just coexisting, but are deeply, functionally integrated. How does the slow grinding of plate tectonics influence the chemistry of the atmosphere? How does the evolution of life alter the weathering of rocks? This synthesis will be the heart of our second half. It represents a move from listing the ingredients to trying to understand the recipe. We will shift from cataloging the parts of the machine to appreciating the logic of the entire interconnected system. But before we get there, we must first explore a few more crucial pieces of the puzzle. We need to understand the intimate conversation between the living world and the atmosphere, and the fundamental rules written in the code of life itself. So let us hold this promise of a coming synthesis and for now, dive deeper into the remarkable agency of the biosphere. Let's turn our attention now to one of the most intimate and powerful conversations on the planet, the dialogue between the biosphere, the world of living things, and the atmosphere. This is not a one-way street where the atmosphere sets the conditions and life simply adapts. Instead, it is a dynamic feedback loop where life actively shapes the sky, and the sky, in turn, shapes life. The most famous example of this, as we've touched upon, is oxygen. For the first half of Earth's history, the atmosphere was virtually devoid of it. It was the invention of photosynthesis by cyanobacteria that slowly, over billions of years, transformed the air into the oxygen-rich mixture we breathe today. This was not a gentle process. It was a radical terraforming of an entire planet by its smallest inhabitants. This single biological innovation created the atmospheric conditions necessary for the evolution of all complex animal life, including ourselves. We live and breathe in an atmosphere constructed by ancient microbes. But the conversation is ongoing, happening right now, all around you. Consider a large forest like the Amazon. A forest is not just a passive collection of trees, it is a powerful engine for climate regulation. Through transpiration, the trees pump enormous quantities of water vapor into the air. This moisture does not just drift away, it creates a feedback loop. The increased humidity makes rainfall more likely. The forest, in a very real sense, generates its own rain. This creates a stable, moist climate that is perfect for the forest's own survival and expansion. It is a self-sustaining system, but it goes even further. The trees also release a cocktail of volatile organic compounds into the air, the chemicals that give a forest its distinctive smell. These chemicals are not just a byproduct, they play a crucial role in the atmosphere. They act as cloud condensation nuclei, tiny particles around which water vapor can condense to form droplets. Without these particles, it would be much harder for clouds and rain to form. So the forest not only provides the moisture for rain, but also the very seeds for the clouds. This is a tight, powerful, balancing feedback loop. More forest leads to a more stable, rainy climate, which is good for the forest. This principle operates in the oceans as well. The surface of the ocean is teeming with phytoplankton, microscopic algae that are the foundation of the marine food web. Like plants on land, they photosynthesize, drawing huge amounts of carbon dioxide out of the atmosphere. When they die, a fraction of them sink to the deep ocean, taking that carbon with them. This biological pump is a critical part of the global carbon cycle, helping to regulate the Earth's climate by sequestering CO2 in the deep sea, where it can remain for centuries. Furthermore, some species of phytoplankton produce a chemical called dimethyl sulfide, or DMS. When DMS is released into the atmosphere, it oxidizes and, just like the chemicals from trees, forms particles that seed clouds. This is another potential feedback loop. Some scientists have hypothesized that in a warmer world, phytoplankton might thrive, produce more DMS, create more bright, reflective clouds over the ocean, which would then cool the planet. This is a version of the Gaia hypothesis in action, a potential planetary-scale thermostat mediated by the smallest of living creatures. In all these cases, we must be careful not to assign intent. The forest does not want to make rain. The phytoplankton are not trying to regulate the climate. Each organism is simply carrying out its own metabolic processes in a way that enhances its own survival. But the collective result of these individual actions, scaled up over an entire biome, creates a powerful, emergent system of regulation. Life is not just adapting to a passive environment. It is actively building and maintaining its own habitat. The conversation between the biosphere and the atmosphere is a constant, creative dance that has shaped the face of our planet. The existence of these powerful feedback loops between life and the atmosphere also implies the existence of thresholds and potential failure modes. These systems are resilient, but they are not infinitely so. Understanding when and how these loops can fail is crucial to understanding the stability of our planet. Let's return to the example of the Amazon rainforest generating its own rain. This is a self-sustaining loop, but it depends on the forest being large and intact enough to produce a sufficient amount of moisture. If large areas of the forest are cleared, its ability to generate rain is diminished. The climate in the region becomes drier, and the fire season becomes longer and more intense. This makes the remaining forest more vulnerable to burning. This is the beginning of a reinforcing or positive feedback loop. Deforestation leads to drying, which leads to more fire and tree death, which leads to more deforestation. Scientists who model this system have warned that there could be a tipping point. If a certain percentage of the rainforest is lost, some estimates put it around 20–25%, the self-sustaining rainfall cycle could break down entirely. At that point, the loop would flip. The drying would become irreversible, and large parts of what is now lush rainforest could transition into a drier, savanna-like ecosystem. The system would shift to a new, stable state, but one that is much less biodiverse and stores far less carbon. This is a classic example of a failure mode. The very feedback loop that maintained the rainforest's resilience can, when pushed past a threshold, become the engine of its collapse. This tipping logic is not dramatic in the sense of a sudden explosion. It is the quiet, inexorable logic of a system crossing a point of no return. We can see similar dynamics in other biomes. Coral reefs are another example. The coral animal lives in a symbiotic relationship with a type of algae that photosynthesizes and provides the coral with most of its food. This partnership builds the vast, complex reef structures that support a quarter of all marine life. However, if the ocean water becomes too warm for too long, the coral becomes stressed and expels the algae. This is coral bleaching. The coral is not dead, but it has lost its primary food source and is highly vulnerable. If the water cools down in time, the algae can return and the reef can recover. The system is resilient up to a point, but if the heat stress is too severe or prolonged, the coral will die and the reef will begin to crumble into rubble. This too can become a reinforcing feedback. A healthy, complex reef structure creates eddies and currents that help to bring in nutrients and cool water. A crumbling dead reef has a much simpler structure and is less able to buffer itself against thermal stress, making it harder for new corals to establish themselves and for the reef to recover. Again, we see a system with a certain capacity for resilience, but which can be pushed past a tipping point into a degraded, alternative, stable state. The implication here is that the health of these biome-atmosphere systems is not a simple, linear function. They can often absorb a surprising amount of disturbance and seem unchanged, which can lull us into a false sense of security. But this apparent stability can mask a gradual erosion of resilience. The system is still functioning, but its buffers are being depleted. When the threshold is finally crossed, the change can be rapid, widespread, and very difficult to reverse. Understanding these failure modes is not about predicting doom. It is about recognizing the hidden logic of the systems we depend on. It is about learning to see the subtle signs of eroding resilience before a threshold is crossed, and appreciating the profound wisdom embedded in these ancient, self-sustaining loops that life has created. Let's now explore another way of looking at life's role in the Earth system using a powerful, if imperfect, analogy. We can think of the fundamental operating principles of life, encoded in DNA, as being similar to a kind of biological software or operating system. This is our sixth evidence track, an analogy that helps us understand the resilience and persistence of life over deep time. Every living organism, from a single bacterium to a giant sequoia tree, runs on a code written in the language of DNA. This code contains the instructions for building the organism's proteins, for carrying out its metabolism, and for creating copies of itself. What is truly remarkable about this code is its stability and its universality. The basic genetic code is essentially the same for all life on Earth, a sign that we all share a common ancestor from billions of years ago. This operating system has been running with continuous updates and modifications for nearly 4 billion years. One of the key features of this biological code is its high fidelity of replication. When a cell divides, it makes an incredibly accurate copy of its DNA. There are sophisticated proofreading and repair mechanisms built into the cellular machinery to catch and fix errors. This is crucial. Without this stability, the genetic instructions would degrade with each generation, and complex life would be impossible. The code is a buffer against the natural tendency toward entropy and disorder. It is a mechanism for preserving information over vast stretches of time. However, the replication process is not perfect. Occasionally, small, random errors, mutations, do occur and are not corrected. Most of these mutations are harmful or neutral, but very rarely a mutation will produce a new trait that happens to be advantageous in the current environment. This is the raw material for evolution by natural selection. This biology as code analogy helps us see evolution in a new light. It is not a random walk, it is more like a learning algorithm. The genetic code of a population is constantly being tested against the environment. The versions of the code that produce more successful, reproducing organisms become more common in the next generation. The code adapts, and we must be explicit about the caveats of this analogy. Unlike computer code, DNA was not designed by an intelligent programmer. Its elegance and complexity are the result of billions of years of blind, unguided trial and error. There is no goal or endpoint to evolution. Furthermore, the relationship between the code, genotype, and the organism, phenotype, is incredibly complex and not as simple as software and hardware. The environment plays a huge role in how the genetic code is expressed. Despite these caveats, the analogy is useful. It frames the biosphere as a planetary-scale information processing system. Over billions of years, life has learned about the Earth's chemistry and physics. It has discovered solutions to incredible challenges: how to capture energy from the sun, how to extract nutrients from rocks, how to survive in extreme heat and cold. These solutions are not stored in a library of books, they are stored in the library of genomes, distributed across all the living organisms on the planet. The biodiversity of the Earth is a living archive of 4 billion years of research and development. It is the accumulated wisdom of the planetary operating system. This perspective helps us understand not just individual organisms, but the deep underlying information architecture that makes the entire living world so resilient and adaptive. Thinking of biology as a kind of adaptive code gives us a powerful frame for understanding resilience. The goal of this operating system is not perfection. In fact, a perfectly rigid and unchanging code would be a fatal flaw. A system that cannot adapt is brittle. It will function perfectly in a stable environment, but it will shatter at the first sign of unexpected change. The resilience of life comes from a delicate balance between stability and flexibility, between high-fidelity replication and the occasional creative error. The system is robust, not flawless. Think of the DNA repair mechanisms in your own cells. They are constantly at work, fixing thousands of errors every single day caused by radiation or chemical damage. They are incredibly good at their job, but they are not perfect. Some errors get through. This imperfection is what allows for evolution, but it also means that systems can fail. This is a fundamental trade-off, A system that allows for adaptation must also allow for the possibility of failure. This principle of graceful failure is a hallmark of resilient systems. When a part of the system breaks, the whole thing doesn't collapse. The damage is contained, and the system can often find ways to work around it. In an ecosystem, if one species goes extinct, other species may be able to step in and fill its role, or the food web may reorganize itself. The ecosystem may be diminished, but it doesn't necessarily suffer a catastrophic collapse. It fails gracefully. This is very different from a complicated, non-adaptive system like a car engine. If you remove the spark plugs, the entire engine stops working. There is no workaround. The interconnectedness and redundancy in a biological system provide this robustness. This framing helps us move beyond a simplistic idea of balance of nature. Nature is not a static, perfectly balanced state. It is a dynamic, ever-changing dance. Its stability is not the stability of a crystal, but the stability of a river, which maintains its identity even as the water within it is constantly changing. The resilience of the biosphere comes from its immense diversity. This diversity represents a portfolio of different solutions to the problem of survival. When the environment changes, some solutions may no longer work, but others might suddenly become highly effective. A warmer climate might be devastating for one species, but it might open up new opportunities for another. The system as a whole adapts because it contains a vast library of pre-existing options. The implication for us is that resilience is not something to be engineered for perfection. It is something to be nurtured by encouraging diversity, redundancy, and adaptability. In our own human systems, from agriculture to economics, we often strive for maximum efficiency by eliminating redundancy and standardizing on a single, perfect solution. This creates brittle systems that are highly productive in a stable world, but are incredibly vulnerable to shocks. The lesson from the biological operating system is that long-term survival depends less on being perfectly adapted to the present moment and more on retaining the flexibility to adapt to an unknowable future. It is a deep and quiet wisdom learned over billions of years of trial and error. Let's now travel back in time again, not just a few million years, but hundreds of millions of years, to a world that would look utterly alien to us. This is our seventh evidence track, the deep time dance of the continents and the profound climatic consequences of their arrangement. Imagine yourself on the shores of a vast, shallow sea about 250 million years ago, near the end of the Permian period. The sun feels hotter, more intense, though the star itself is slightly dimmer than it is today. The air is thick, hazy, and low in oxygen. The vegetation on land is strange and unfamiliar. No flowers, no grasses, just forests of hardy seed ferns and conifers. But the most striking feature of this world is not the life, but the geography. All of the Earth's major land masses are gathered together into a single, colossal supercontinent. We call it Pangea. From your vantage point, you could, in theory, walk from the land that will one day become Antarctica across the future Africa and North America, all the way to the future Siberia, without ever crossing a major ocean. The rest of the planet is a single, world-spanning ocean called Panthalassa. This is a world of profound geographic simplicity compared to our own. What would it feel like to live in the interior of this supercontinent? It would be a climate of unimaginable extremes. The sheer size of Pangea meant that its heartland was thousands of miles from the moderating influence of the ocean. The oceans, remember, are our planet's great thermal buffer. They absorb heat slowly and release it slowly, dampening temperature swings. Without this influence, the center of Pangea would have experienced brutal seasons. Summers would be scorching hot, likely reaching temperatures far higher than anything on Earth today. Winters would be bitterly cold. Even more importantly, this deep interior would have been incredibly arid. The source of all rain is evaporation from the ocean. The storm systems that carry this moisture can only penetrate so far inland. The heart of Pangea would have been a vast desert, larger than any that exists today, a place hostile to all but the most specialized and hardy forms of life. The coastlines of Pangea would have been subject to colossal mega-monsoons, as the massive continent heated up in the summer, drawing in huge amounts of moisture from the Panthalassic Ocean, leading to seasons of torrential rain. It was a world of climatic superlatives. The slow process of plate tectonics is the engine that drives this continental cycle. The Earth's mantle is constantly churning, like a thick pot of soup on a slow boil. This motion pulls some continents apart, opening new ocean basins, and smashes others together, raising up mountain ranges. Over hundreds of millions of years, this dance leads to a recurring cycle of supercontinent assembly and breakup. We can see the evidence of Pangea's existence in the fossil record. The same land animals and plants are found in South America and Africa, for instance, and in the geological fit of the continents. Pangea was not the first supercontinent, and it will not be the last. In another couple of 100 million years, the continents will likely reassemble into a new configuration. Rebuilding this unfamiliar world in our minds serves a crucial purpose. It breaks us out of the assumption that the world has always looked the way it does now. It demonstrates that the planet's fundamental geography, the very map of the world, is a variable, not a constant. And as we will now see, changing the map has profound consequences for the entire Earth system. The assembly and breakup of supercontinents like Pangea have massive implications for the global climate and for the evolution of life. These geographic arrangements are not just a backdrop, they are a primary driver of the entire Earth system. First, let's consider the impact on ocean circulation. In our modern world, with its many continents and smaller ocean basins, we have a complex system of ocean currents that acts like a global conveyor belt. Warm surface water from the tropics flows toward the poles, releases its heat to the atmosphere, becomes colder and denser, sinks to the deep ocean, and then flows back to the tropics. This circulation is a critical mechanism for transporting heat around the planet, preventing the equator from getting too hot and the poles from getting too cold. In the world of Pangea, with one giant ocean, this circulation would have been very different. Models suggest it would have been much more sluggish. The deep ocean may have become stagnant and anoxic, that is, devoid of oxygen. This would have had huge consequences for marine life and also for the chemistry of the entire planet. A stagnant, anoxic ocean can release large amounts of toxic gases like hydrogen sulfide, which can be devastating for life both in the sea and on land. The geography of the continents directly controls the plumbing of the global heat transport system. Second, the formation of a supercontinent changes the overall sea level. When continents are spread apart, the young, hot and buoyant ocean crust at the mid-ocean ridges displaces a lot of water, leading to higher sea levels and shallow seas that flood the continental interiors. When a supercontinent forms, the old, cold, dense oceanic crust subducts. The average age of the seafloor increases and the ocean basins become deeper, causing sea levels to fall. This exposes vast areas of continental shelf. These long-term changes in sea level, driven by the tectonic cycle, dramatically alter the amount of land versus ocean, which in turn affects the climate through changes in how much sunlight is absorbed or reflected. Third, and perhaps most importantly, the supercontinent cycle has a direct impact on the carbonate-silicate cycle, the long-term planetary thermostat we discussed earlier. The weathering of rocks, which removes CO2 from the atmosphere, happens most efficiently in warm, wet, and mountainous regions. The assembly of a supercontinent can create massive mountain ranges where the continents collide, temporarily increasing weathering rates. However, the vast, arid interior of the supercontinent would have experienced very little chemical weathering, slowing the process down. Furthermore, the total length of coastline is dramatically reduced in a supercontinent configuration, which also reduces the area where moist ocean air can interact with continental rocks. The net effect of these changes on the global carbon cycle is complex and a subject of ongoing research, but it is clear that continental geography is a first-order control on the planet's long-term climate regulator. The harsh interior climate and altered ocean chemistry of the Pangean world likely contributed to the Great Dying, the Permian-Triassic extinction event, which happened around the time Pangea was fully assembled. It was the most severe extinction in Earth's history, wiping out over 90% of marine species and 70% of terrestrial vertebrate species. While the primary trigger is thought to have been a massive volcanic eruption in Siberia, the background conditions created by the supercontinent, the harsh climate, the anoxic oceans, likely made the biosphere much more vulnerable to this shock. The system's resilience had been eroded by its geography. This deep time perspective shows us that even the solid ground beneath our feet is part of a dynamic cycle that shapes our world in the most fundamental ways. Now let's once again adopt the mindset of a friendly skeptic. We have built a picture of a complex, interconnected, and resilient Earth system. What are the strongest criticisms of this view, and what evidence could potentially falsify it? Engaging with these questions is not a sign of weakness in the theory, but a necessary part of honest scientific inquiry. The most fundamental criticism, as we touched on in our objections section, is the argument from luck, also known as the anthropic principle. The argument is that we shouldn't be surprised to find ourselves on a planet with a long, stable history, because we could not have evolved on one without it. If the Earth's regulatory systems were not effective, we simply wouldn't be here to observe them. Therefore, concluding that the Earth's stability is a special or emergent property of a complex system might be a logical error. It might just be that we are the beneficiaries of an incredibly unlikely series of fortunate events. It's not a system, it's a winning lottery ticket. A second major criticism focuses on the role of contingency in Earth's history. The paleontologist Stephen Jay Gould famously argued that if you were to replay the tape of life, the result would be completely different every time. A single, contingent event, a slightly larger asteroid, a volcanic eruption lasting 1,000 years longer, the evolution of a particularly virulent microbe, could have sent the planet down a completely different path, one that did not lead to us or anything like us. This view emphasizes the chaotic and unpredictable nature of history over the stabilizing influence of feedback loops. In this view, the resilience we see is an illusion, a temporary state of calm in a fundamentally chaotic universe. The feedback loops might provide some stability, but they are easily overwhelmed by random catastrophic events. So, what kind of discovery could falsify or seriously weaken the self-regulating Earth model? Here are a few potential falsifiers presented as pros. One would be the discovery of a planet in another solar system that is virtually identical to Earth in size, composition, and distance from its star, but which is clearly sterile and has a runaway climate, like Venus. If we found many such Earth twins that had failed, it would strongly support the idea that Earth's success is due to luck rather than an inherent property of Earth-like planets. It would suggest that the regulatory systems are not a robust feature, but a fragile and rare outcome. Another falsifier would be a major revision of our understanding of Earth's history that showed long periods where life was absent or minimal, yet the climate remained stable. If the planet could regulate itself just fine without a significant biosphere, it would severely weaken the Gaian argument that life is a critical component of the regulatory system. It would suggest that geology and chemistry are doing all the work, and life is just along for the ride. A third would be the discovery that one of the key proposed balancing feedbacks does not work as we think it does, or that it is, in fact, a reinforcing feedback. For example, if further research showed that the cloud-seeding chemical DMS produced by phytoplankton ultimately leads to a net warming effect rather than a cooling one, it would undermine one of the classic examples of a biological feedback loop. Science is constantly testing and re-evaluating these mechanisms, and our understanding of them could change. Finally, we must concede where the model is weakest. The strong Gaia hypothesis, which verges on suggesting the Earth is a goal-directed superorganism, is very difficult to test and is not widely accepted. The model is also less effective at explaining the very rapid, non-linear shifts in the Earth system, like the tipping points we've discussed. While it can describe the conditions that lead to them, the precise timing and nature of these shifts are often chaotic and unpredictable. Conceding these points and actively looking for falsifying evidence is what separates a robust scientific framework from a rigid ideology. It keeps the inquiry open and honest. Let's take a brief interlude from the evidence itself and turn our attention back to the method of our inquiry. We are piecing together a story from incomplete layers of information, much like a detective trying to solve a case with only a handful of clues. This requires a certain mindset, an awareness of how our own assumptions and the nature of the evidence shape the picture we create. Our starting point is always our prior belief, or prior. Before we even look at the evidence, we have a model in our head of how the world works. A scientist trained in the reductionist tradition of physics and chemistry might have a prior belief that the world is best understood by breaking it down into its component parts. A biologist might have a prior that emphasizes the agency and adaptability of life. Neither of these is wrong, but they are different starting points that will cause them to pay attention to different kinds of evidence. Part of our work tonight is to remain aware of our own priors, to question whether we are seeing the system as it is, or as our background assumptions predispose us to see it. Then we encounter the evidence itself, the layers of data from ice cores, geology, and atmospheric chemistry. The key here is to pay attention to anomalies. An anomaly is a piece of data that doesn't fit the prevailing model. It's the clue that doesn't make sense. For a long time, the extreme chemical disequilibrium of Earth's atmosphere was an anomaly. Given the laws of chemistry, the atmosphere shouldn't look the way it does. Instead of ignoring this anomaly, scientists like James Lovelock focused on it, and it became the cornerstone of the Gaia hypothesis. The anomaly was not an error, it was a signal that the existing model was incomplete. A good detective and a good scientist loves anomalies. They are the engines of curiosity and the signposts toward a deeper understanding. We must also be constantly aware of the problem of erasure. The geological record, as we've noted, is a story with most of its pages ripped out. What is not preserved? Generally, the record is biased toward preserving large, slow, widespread events. Small, rapid, localized events are much less likely to leave a trace that survives for millions of years. This means our picture of the past is inherently smoothed out and simplified. We might be missing entire chapters of the story, entire modes of being that the Earth system once possessed, simply because they did not leave behind a durable record. We must be humble about the possibility that the past was far stranger and more dynamic than our limited evidence suggests. This detective mindset requires a comfort with uncertainty. We are not trying to prove a single story beyond a shadow of a doubt. We are trying to find the most plausible story that fits the available, incomplete evidence. This means holding multiple hypotheses in our minds at once and being willing to update our beliefs as new evidence comes to light. It is a process of gradual approximation, of slowly building a clearer picture while always knowing that the picture will never be perfectly complete. With this renewed appreciation for the challenges of our method, we can now reopen our main thread. We return to the evidence not with a sense of false certainty, but with the quiet confidence of a detective who understands the limits of their tools, yet continues the search for a deeper truth, guided by curiosity and a respect for the complexity of the case. After our journey through deep time, celestial mechanics, and the abstract world of systems theory, let's bring our awareness back to the human scale. Let's ground ourselves once again in the immediate, tangible reality of this room and of your own body. Feel once more the gentle rhythm of your breath, in and out. Each breath is a quiet affirmation of your membership in the planetary system. You are drawing in the oxygen that was gifted to the atmosphere by ancient cyanobacteria and is replenished daily by the forests and phytoplankton of the world. With each exhale, you release carbon dioxide, a molecule that will be taken up by a nearby plant, or will dissolve in the ocean, or will remain in the atmosphere, playing its small part in the planet's thermal balance. You are not separate from these cycles. You are a participant. Your own body is a node in this vast, interconnected network. Bring your attention to the feeling of the temperature of the air on your skin. Your body is a warm-blooded mammal, a finely tuned engine that maintains a constant internal temperature of around 37 degrees Celsius, or 98.6 degrees Fahrenheit. This ability, called endothermy, is a remarkable evolutionary innovation. It is your own personal biological buffer against the temperature swings of the external world. Your metabolism is constantly working, burning fuel to generate heat, or activating cooling mechanisms like sweating to keep your internal environment stable regardless of whether the world outside is hot or cold. You are, in yourself, a small self-regulating system. This personal stability gives you a profound sense of agency, but it's an agency that operates within the constraints of the larger system. You can choose to put on another blanket if you are cold, or open a window if you are warm. These are small acts of personal climate regulation. You are adjusting the buffers of your immediate environment to assist your own biological systems. This is not a trivial observation. It highlights a fundamental principle. We exist in a nested hierarchy of regulatory systems. Your body's internal thermostat is nested within the microclimate of your room, which is nested within the weather of your region, which is nested within the global climate system. Each level provides a degree of stability and buffering for the level within it. This reset to the human scale is not an escape from the complexity we've been exploring. It is a reminder that this complexity is not just an abstract, external phenomenon. It is personal. It is embodied. The sense of peace and safety you may be feeling right now is a direct result of this nested stability. Your body is stable. Your room is stable. And the planet, for now, is stable enough to allow for this moment of quiet rest. There are no prescriptions here, no calls to action. It is simply an invitation to feel your own existence as part of this layered, resilient, and interconnected world. You are in the loop. You belong to the system. Let's now turn to our eighth and final track of evidence, which deals with the most fundamental currency of the universe, energy. Every process we have discussed, from the spin of the planet to the metabolism of a single cell, is governed by the flow of energy. Understanding the Earth's energy budget, the balance between incoming and outgoing energy, is key to understanding its climate and stability. The Earth's primary source of energy is the sun. Solar radiation arrives at the top of the atmosphere with an intensity of about 1,160 watts per square meter. This is known as the solar constant, though it does vary slightly over time. Because the Earth is a sphere, and because of the day-night cycle, the average amount of energy spread over the entire surface is only 1/4 of this, or about 340 watts per square meter. This is our incoming energy budget. For the planet's temperature to remain stable over time, this incoming energy must be balanced by an equal amount of outgoing energy. The first thing that happens to this incoming solar energy is that some of it is immediately reflected back to space. About 30% of the sunlight that reaches Earth is bounced off the tops of clouds, off bright surfaces like ice and snow, and even off the atmosphere itself. This reflectivity is known as the Earth's albedo. The remaining 70% is absorbed by the planet, by the atmosphere, the land and the oceans, warming them up. To balance this absorbed energy, the Earth must radiate energy back out into space. It does this in the form of long-wave infrared radiation, or heat. This is where the greenhouse effect, which we've discussed, becomes so critical. If there were no atmosphere, the Earth's surface would radiate this heat directly into space, and the planet would be frozen. But the greenhouse gases in our atmosphere intercept much of this outgoing heat and re-radiate it in all directions, including back down toward the surface. This process is what keeps the surface warm enough for liquid water. The atmosphere acts as a gatekeeper, letting the shortwave solar energy in, but impeding the long-wave heat energy from getting out. The parameters of this energy budget set the fundamental constraints for the entire Earth system. A small change in any of the key variables can have significant consequences. If the sun's output were to increase, the incoming energy would go up. If a series of large volcanic eruptions filled the stratosphere with reflective sulfate aerosols, the albedo would increase, reflecting more sunlight and cooling the planet. If the concentration of greenhouse gases in the atmosphere increases, the outgoing energy is reduced, and the planet must warm up to a new, higher temperature where the outgoing energy once again balances the incoming. This energy budget framework allows us to quantify the impact of different processes. We can measure the radiative forcing, the change in the energy balance, caused by adding a certain amount of carbon dioxide to the atmosphere, or by a change in cloud cover, or by deforestation that replaces a dark forest with lighter-colored pasture. It provides a common currency for comparing the impact of wildly different phenomena. This perspective reveals the climate system as fundamentally an energy processing engine. The weather patterns, the ocean currents, the storms and winds, these are all part of the system's vast, chaotic, and beautiful mechanism for moving energy from the tropics, where there is an energy surplus, toward the poles, where there is an energy deficit. It is all driven by the simple, relentless physics of energy-seeking equilibrium. The consequences of this flow are the world we experience, the climate, the seasons, and the conditions that make life possible. The energy budget framework is not just a descriptive tool, it is a predictive one. It allows us to perform sensitivity analyses asking what-if questions about the climate system. What if we double the amount of carbon dioxide in the atmosphere? The basic physics of the energy budget tells us that this will trap a certain amount of extra energy, leading to warming. The much more difficult question is, how much warming? This is where the second-order trade-offs and the complexities of the feedback loops come back into play. The initial warming from the CO2 is just the first step. The system will respond to this warming in ways that can either amplify or dampen it. For example, as we've discussed, a warmer world means more water vapor in the atmosphere. Since water vapor is a powerful greenhouse gas, this is a strong amplifying feedback. A warmer world also means less ice and snow, which lowers the planet's albedo, causing it to absorb more sunlight, another amplifying feedback. Then there are the much more uncertain feedbacks, particularly those involving clouds. Will a warmer world have more of the low, thick, reflective clouds that cool the planet, or more of the high, thin, cirrus clouds that tend to trap heat and warm it? Small changes in the type and amount of cloud cover can have a huge impact on the energy budget, but clouds are notoriously difficult to simulate in global climate models. This uncertainty about clouds is one of the main reasons why different models give a range of predictions for future warming. This sensitivity analysis reveals that there are multiple plausible mechanisms that could lead to different outcomes. The final state of the climate is not determined by a single factor, but by the complex interplay of numerous feedbacks. We can create an uncertainty budget to identify which parts of the system we understand well, like the direct warming effect of CO2, and which parts are still poorly understood, like the cloud feedback. This is a crucial part of the scientific process. It tells us where we need to focus our research efforts. This perspective also highlights the trade-offs inherent in the system. A world with a strong greenhouse effect is warm enough for liquid water, which is good for life, but that same greenhouse effect also makes the climate sensitive to changes in the composition of the atmosphere. The very thing that makes the planet habitable also makes it vulnerable to a certain kind of change. There is no perfect, risk-free design. The Earth's climate is a product of these evolutionary trade-offs, a system that works but that has inherent sensitivities and vulnerabilities. Understanding this helps us move away from a search for simple, single causes and toward an appreciation of the complex, interconnected nature of the whole system. The final temperature of the planet is not a simple knob we can turn up or down. It is an emergent property of a system that is sensitive to our actions in ways we are still struggling to fully comprehend. As we trace the intricate patterns of the Earth system through the lens of modern science, it is worth pausing to acknowledge that we are not the first humans to try and make sense of these vast, powerful forces. For thousands of years, cultures around the world have developed their own ways of mapping these patterns through myth, story, and cosmology. This cultural lens offers a different, but not necessarily contradictory, way of understanding our place in the world. Many ancient cultures saw the world not as a machine, but as a living entity, or as a place animated by a multitude of living spirits. The earth was often personified as a mother goddess, Gaia in Greece, Pachamama in the Andes, Prithvi in India. This was not just a poetic metaphor, it reflected a deep, intuitive understanding of the planet as a source of all nourishment, a life-giving and self-sustaining presence. This worldview fostered a sense of kinship and reciprocity with the natural world. Humans were not masters of the earth, but the youngest children of a much older and wiser being. We can see echoes of the scientific patterns we've discussed in these older narratives. The cyclical nature of time, so fundamental to the Earth's stability, is a core theme in many mythologies. The wheel of the year in Celtic traditions, the cycle of death and rebirth in Egyptian myths of Osiris, the Hindu concept of yugas or world ages, all of these reflect a deep observation of the rhythmic, repeating patterns of nature, the seasons, the life cycles of plants, the phases of the moon. These stories mapped the temporal buffers of the world into a human, meaningful narrative. The idea of a world held in a delicate balance is also a common theme. In Norse mythology, the world tree Yggdrasil connects the different realms, and its health is essential for the stability of the cosmos. In many indigenous traditions, the world is maintained by a series of reciprocal relationships and rituals between humans and the more-than-human world. If humans take too much or fail to perform the proper ceremonies, the balance will be upset, leading to drought, famine, or floods. This can be seen as a narrative expression of feedback loops. It is an understanding that human actions have consequences that ripple through the entire system, and that maintaining stability requires attention, respect, and restraint. Of course, we must be modest in our claims when drawing these parallels. Ancient myths are not scientific theories in disguise. They are complex, multi-layered narratives that served a wide range of social, psychological, and spiritual functions. But it is not a coincidence that so many cultures observing the same world arrived at a picture that emphasized interconnectedness, cyclical time, and a living, responsive Earth. They were using the tools they had, story, metaphor, ritual, to map the same fundamental reality that we are now mapping with the tools of satellite data and mass spectrometry. This cultural lens reminds us that scientific knowing is not the only way of knowing. It invites us to see our modern, systemic view of the Earth not as a radical new discovery, but as a rediscovery in a new language of a very old and very deep human wisdom. We have now traveled along many different paths. We have explored the simple, human-scale buffers of shadow and rotation. We have delved into the complex feedback systems of the atmosphere. We have looked to the sky to understand the stabilizing dance of the moon, and deep into the Earth's crust to read its ancient archives. We have seen how life itself is a planetary force, shaping its own environment, and how the very code of life is a testament to resilience. We have witnessed the slow waltz of the continents and tallied the planet's fundamental energy budget. We are now standing with all these threads in our hands. The next step in our journey is to begin weaving them together, to move from the individual instruments to the sound of the entire orchestra. Soon we will attempt to reframe these separate ideas into a single, more unified understanding. The time has come for the turn. Throughout our journey, we have often spoken in binaries, stable versus unstable, life versus non-life, simple versus complex. These distinctions have been useful for building our understanding, but they are ultimately just scaffolds. The deeper truth of a complex system lies not in the binaries, but in the continuum between them. The turn is a shift in perspective, a move to dissolve these false dichotomies and embrace the nuanced, interconnected reality of the whole. Let's start with the binary of a habitable versus uninhabitable planet. We often talk about the habitable zone around a star as if it were a clearly defined region where a planet either is or is not suitable for life. But our exploration has shown that habitability is not a simple yes-no property. It is a spectrum. Earth is not just in the habitable zone, it has actively widened and maintained its place within it. Through biological and geological feedbacks, the Earth has kept its climate within a life-permitting range even as the sun has grown brighter over billions of years. Habitability is not a state that a planet is in. It is a process that a planet does. It is an emergent property of the entire co-evolving system. This reframing moves us from a static to a dynamic view. A planet is not a house waiting for a tenant. It is a garden that is cultivated over geological time by the interplay of life and geology. This has profound implications for our search for life elsewhere in the universe. We might need to look not just for planets with the right initial conditions, but for planets that show signs of long-term systemic regulation. Now let's dissolve the binary between the living and the non-living. We tend to draw a sharp line between a rock and a bacterium, between geology and biology. But where does that line really exist? The oxygen in our atmosphere is a product of life. The limestone that makes up vast mountain ranges is the skeletal remains of trillions of living creatures. The soil beneath our feet is an intricate mix of eroded rock and decaying organic matter. Life has not just adapted to the geology of Earth, it has become the geology of Earth. The biosphere and the geosphere are so deeply intertwined that they are no longer separable. They are two components of a single integrated system. This wider model asks us to see the world not as a collection of separate objects, but as a network of processes. A tree is not just a thing, it is a process of turning sunlight, water, and air into wood and sugar. A mountain range is not a static object. It is a process of tectonic uplift and erosional decay. Your own body is not a fixed entity. It is a process of constant renewal, a standing wave of matter and energy. What does this turn mean for us in our lived experience? It replaces the feeling of being an isolated individual on a passive planet with a sense of being an integral part of a vast, dynamic, and evolving whole. The choice is not between acting on the world or being acted upon by it. The reality is that we are constantly and unavoidably participating in its processes. Our breath, our food, our every action is a transaction with the planetary system. This is not a burden of responsibility, but an invitation to a deeper sense of belonging. The binary of humanity versus nature dissolves. We are not separate from nature. We are one of its more recent and particularly potent expressions. The turn is a quiet homecoming, a realization that the world is not something we look at, but something we are. With this new, continuous perspective in hand, let's attempt our first pass at a synthesis. How do we integrate these various evidence tracks from the micro to the macro into a minimal, coherent model of a self-regulating Earth? Our model begins with a constant external input, energy from the sun. This energy drives every process on the planet. The first layer of regulation, as we saw, is mechanical and astronomical. The Earth's rotation distributes this energy, creating the day-night cycle. The Earth's axial tilt, stabilized by the Moon, distributes it further, creating the seasons. These are the coarse primary controls, the planetary scale hardware that establishes the fundamental rhythms of the system. They are the slow, steady drumbeat to which the rest of the planet dances. The next layer is geochemical. The atmosphere and the oceans act as the planet's circulatory system and its thermal flywheel. They absorb the incoming energy and transport it around the globe, smoothing out the temperature differences between the equator and the poles. Within this geochemical system are the key feedback loops that act as the long-term thermostat. The most important of these is the carbonate-silicate cycle, a slow geological process that regulates atmospheric carbon dioxide over millions of years, keeping the planet's temperature within a relatively stable range. This is the deep, underlying software of the climate, the background process that has prevented the planet from tipping into a permanent snowball or a runaway greenhouse state. The third, and perhaps most transformative layer, is biological. Life did not just arise within this pre-existing system, it began to actively participate in and modify it. The invention of photosynthesis by microbes fundamentally re-engineered the planet's chemistry, creating our oxygen-rich atmosphere. This new atmosphere, in turn, allowed for the evolution of new, more complex forms of life. This is the great co-evolutionary dance. Life shapes the planet, and the shaped planet creates new possibilities for the evolution of life. In this synthesis, biomes like forests and the phytoplankton in the oceans are not just passive inhabitants. They are key components of the regulatory machinery. They create their own microclimates. They actively participate in the global carbon and water cycles. They are like sophisticated, self-replicating modules that plug into the planet's geochemical operating system and add new layers of regulation and resilience. The genetic code of all life, with its blend of stability and adaptability, provides the underlying information architecture for this process. It is the mechanism by which the biosphere learns and remembers solutions that work. This minimal model connects the micro to the macro. The metabolic process inside a single bacterial cell, when multiplied by trillions and sustained over millions of years, can change the composition of an entire planet's atmosphere. The slow, inexorable drift of a tectonic plate, by changing ocean currents and weathering patterns, can alter the evolutionary path of every organism on the surface. Everything is connected across all scales of time and space. This is not a model of top-down intelligent design. There is no central controller. Instead, it is a model of bottom-up, emergent order. The stability we observe is a product of this multi-layered, interconnected network of feedback loops, developed and refined over 4 billion years. It is a system that has grown, not been built. Its resilience comes not from rigid control, but from its diversity, its redundancy, and its capacity for adaptation. It avoids triumphalism because it acknowledges that this system is not perfect. It has had catastrophic failures in the past, and it has inherent vulnerabilities. It is simply the system that has, so far, endured. Our synthesis would be incomplete and dishonest if we did not explicitly acknowledge what remains unknown and how we reconcile the counterpoints we have raised. A mature understanding of any complex system involves not just knowing what we know, but having a clear map of the boundaries of our ignorance. First, let's reconcile the central tension between the self-regulating system view and the lucky accident view. The most reasonable synthesis is that it is not an either-or question. The truth likely lies in a combination of both. The initial conditions for Earth were almost certainly lucky. Being the right size in the right orbit, with the right chemical constituents, these were likely prerequisites, a winning hand in the cosmic lottery. However, once life got started, it did not remain a passive passenger. It began to influence the planet, and feedback loops, both biological and geological, emerged that enhanced and maintained that initial habitability. So it was luck that got the game started, but it was the emergence of a self-regulating system that has kept the game going for 4 billion years. It is a story of chance and necessity intertwined. Next, we must be explicit about the largest areas of uncertainty. As we've noted, the role of clouds is a major one. We do not have a complete theory of how the global cloud cover will respond to a warming world, and this represents the largest source of uncertainty in future climate projections. Another huge unknown is the deep biosphere. We now know that there is a vast amount of life, perhaps more, by mass, than all the life on the surface, living deep within the Earth's crust and ocean sediments. These microbes are living incredibly slowly on timescales of thousands of years. We have almost no understanding of what role this deep biosphere plays in the planet's major geochemical cycles. It is a vast, dark continent of ignorance. We must also be clear about the limits of our models. Our computer models of the Earth system are incredibly sophisticated, but they are still profound simplifications of reality. We cannot model every single tree, every single bacterium, every single cloud droplet. We have to make approximations and parameterizations. This means the models are good at capturing the large-scale, long-term behavior of the system, but they can struggle to predict the timing and location of specific, short-term events. They are like a blurry photograph of the future, not a crystal ball. So, how do we move forward? The next tests for this synthesized model will come from several areas. The ongoing exploration of Mars and Venus will provide crucial comparison points, helping us understand why their planetary histories diverged so dramatically from Earth's. The search for exoplanets, and especially the analysis of their atmospheres, will, for the first time, give us a statistical sample of other worlds, allowing us to see if the features of our Earth system are common or rare. And, in a tragic and uncontrolled way, our own ongoing experiment of rapidly changing the Earth's atmosphere will provide a stark and definitive test of the system's resilience and its tipping points. The map of our next tests, then, is a map of our current unknowns. We name what remains uncertain not as a sign of failure, but as a guide for future inquiry. It is the humility at the heart of the scientific process, the open admission that our most sophisticated understanding is still just a preliminary sketch of a reality that is far more complex and wonderful than we can fully imagine. To bring this grand synthesis down to a more tangible level, let's walk through one final case study, placing you within a vivid, step-by-step chain of causality that weaves together all our threads. Imagine you are a single carbon atom. For the last few centuries, you have been part of a carbon dioxide molecule, drifting in the vast, turbulent expanse of the Earth's atmosphere. You are part of the planet's greenhouse blanket, vibrating as you absorb and re-radiate heat from the surface below. Your journey is governed by the grand circulation of the atmosphere, carried by the trade winds, lifted in towering columns of convection over the tropics. This is the world of systems, feedbacks, and energy budgets. One day your journey takes you over the North Atlantic Ocean. The surface of the water is cold and churning. You dissolve into the ocean, becoming part of the planet's vast chemical buffer. Here, you might remain for hundreds of years, pulled down into the deep ocean as part of the global conveyor belt circulation we spoke of. But your journey takes a different turn. You are near the surface, where there is sunlight. A microscopic organism, a coccolithophore, absorbs you. This is the moment you cross the threshold from the non-living to the living. Inside this single cell, through the magic of photosynthesis, a process encoded in DNA, refined over billions of years, the energy of the sun is used to break apart your CO2 molecule. Your carbon atom is used to build a sugar molecule, the fuel for the cell's life. This is the biological layer in action, life actively pulling you out of the atmosphere and ocean. But the coccolithophore does something else. It combines you with calcium ions in the water to build a series of intricate, beautiful plates of calcium carbonate, chalk, that form a protective shell around it. You are no longer just part of a soft, biological molecule. You have become part of a mineral. You have become geology. The coccolithophore lives its short life and then it dies. Its organic parts are consumed by other bacteria, but its tiny, chalky shell containing you begins to sink. It joins a slow, constant snow of similar shells, falling from the sunlit surface waters into the dark, cold abyss. Your journey takes you down, mile after mile, until you settle on the ocean floor. Here you join a thick layer of ooze, the accumulated remains of trillions of organisms that have lived and died before you. This is the planet's archive, its memory, Over millions of years, the pressure of the layers above you and the heat from the Earth's interior compress this ooze, turning it into solid rock. You are now part of a layer of limestone in the Earth's crust. This is the end point of the carbonate-silicate cycle. Your journey has taken you from the atmospheric greenhouse to a stable, long-term geological storage. But the story is not over. The tectonic plate you are a part of is moving at the speed your fingernails grow. Over tens of millions of years, it drifts across the planet. Eventually, it collides with another continent. The immense forces of this collision buckle and lift the seabed. The limestone layer you are in is thrust upwards, thousands of feet into the air, becoming part of a new mountain range. For thousands of years, you are locked in the rock. But slowly the forces of erosion, the wind and the rain, begin to wear the mountain down. One day, a droplet of acidic rainwater containing CO2 from the atmosphere dissolves the rock around you, releasing you once again. You are washed into a river and carried back to the ocean, perhaps to be taken up by another organism, or perhaps to be released back into the atmosphere as carbon dioxide, ready to begin the entire epic cycle all over again. Your single journey as one atom has woven together every theme we have explored: energy flows, planetary cycles, the agency of life, deep time, and the archives of geology. You are not just on the Earth, you are of the Earth. So where does this grand, systemic understanding leave us? Does it leave us as powerless observers of a vast machine, or does it offer a path toward a more conscious and skillful participation? The practical translation of this perspective is not a list of grand, heroic actions, but a series of small, testable practices for our own attention and agency, framed with a local first perspective and without moralizing. The first practice is simply to cultivate a deeper awareness of the buffers in your own life. When you drink a glass of clean water from your tap, take a moment to consider the vast system that delivered it. The clouds that transported the moisture from the ocean, the soil that filtered it, the aquifer that stored it, the infrastructure that brought it to your home. You are at the end of a long chain of natural and human-made buffers. Appreciating this doesn't require any action. It is simply a way of seeing, of recognizing your profound dependence on systems that are largely invisible. This practice of systems gratitude can gently shift your perspective from one of individual self-sufficiency to one of interconnected dependence. A second practice is to notice the timescales. In our daily lives, we are often trapped in the timescale of immediate urgency. Try for a moment to consciously inhabit a different timescale. Look at a large, old tree and consider the hundreds of seasons it has weathered. Look at a stone and consider the geological journey that brought it to be in your hand. Or simply notice the slow, gradual change of the seasons in your own neighborhood. By consciously shifting your temporal focus, you are exercising a kind of mental muscle. You are training your mind to see beyond the immediate moment and to connect with the deeper, slower rhythms of the world. This can be a powerful antidote to anxiety and the feeling of constant crisis. It doesn't erase problems, but it places them in a much larger and more stable context. A third practice involves small-scale experimentation with your own local buffers. This could be as simple as planting a native tree or starting a small garden. In doing so, you are not just beautifying a space, you are participating in the local water cycle. You are creating a small patch of shade and evaporative cooling. You are providing a habitat for pollinators. You are creating a tiny, local node of increased resilience in the wider system. These actions are not about saving the planet. They are about engaging in a reciprocal relationship with your own place. They are about translating a global understanding into a local, tangible practice. These practices are not meant to be a burden. They are invitations. They are small ways to test and feel the reality of the interconnected world we have been exploring. They are grounded in the idea that agency begins with attention. By changing what we pay attention to, we change our relationship with the world. We move from seeing ourselves as isolated subjects in a world of inert objects to feeling ourselves as active participants in a living, dynamic system. The goal is not to fix the world, but to find our own skillful and attentive place within it. As we look toward the future, this systems perspective provides a framework for thinking about plausible scenarios and for identifying the most important, open questions. This is not about prediction, which is impossible in a complex system, but about bounded speculation, exploring the range of possibilities based on our understanding of how the system works. One plausible scenario is that the Earth system, pushed by human activities, will cross one or more tipping points and transition to a new, much warmer, hothouse state. In this scenario, reinforcing feedbacks like the melting of permafrost and the loss of the Amazon rainforest would take over, creating a self-sustaining warming trend that would be very difficult for humanity to reverse. This would not be the end of the world, and it would probably not even be the end of life on Earth. The planet has been in hothouse states before, but it would be a world with a dramatically different climate, with much higher sea levels, and it would be profoundly challenging for our current global civilization. Our confidence that this scenario is possible is high, though the exact timing and nature of the tipping points are very uncertain. Another plausible scenario is that the system is more resilient than we think, or that we as a global society act quickly and effectively enough to avoid the worst tipping points. In this scenario, the balancing feedbacks, though stressed, would hold. The planet would warm, and we would see significant changes in weather patterns and sea levels, but the system would eventually restabilize at a new, warmer equilibrium. This scenario would still represent a massive challenge, but it is one that is more manageable. Our confidence in this scenario depends critically on the actions that we take in the coming years and decades. This leads to the most important open questions for the future. First, where are the tipping points? Scientists are working urgently to identify the thresholds for key systems like the Greenland ice sheet, the Atlantic Ocean circulation, and major forest biomes. Knowing where these lines are is critical for understanding the risks we face. Second, how interconnected are these tipping points? It's possible that tipping one system, like Arctic sea ice, could increase the likelihood of tipping another, like the Greenland ice sheet, creating a tipping cascade. Understanding these potential domino effects is a major priority. Third, and most hopefully, are there positive tipping points? Could a rapid social or technological shift, a breakthrough in clean energy, a global movement toward ecological restoration, create a reinforcing feedback loop in the human system that could rapidly bend the curve away from the worst outcomes? Thinking about the future in this way moves us beyond simple optimism or pessimism. It is a pragmatic, clear-eyed assessment of the dynamics at play. The future is not a predetermined path. It is a landscape of possibilities with different pathways that become more or less likely depending on the choices we make and the behavior of the system itself. We are navigating this landscape with an incomplete map, but the principles of systems thinking give us the best available compass. We must label our confidence levels, acknowledge our uncertainties, and focus our attention on the critical question: how do we build resilience in both our human and our ecological systems to navigate the turbulent times ahead? Having journeyed through the intricate mechanics and vast timescales of the Earth system, let's pause and allow this intellectual model to settle into a felt meaning. What does it feel like to inhabit this understanding of the world? The first feeling might be one of profound awe. It is the awe of recognizing the sheer, improbable elegance of the system that supports us. To know that the air you breathe was crafted by microbes, that the stability of your seasons is a gift of a distant moon, that your own atoms have cycled through rock and sea and life for billions of years. This is to see the world not as a collection of ordinary things, but as a place of constant, quiet miracle. It replaces a mundane, disenchanted view of reality with one that is rich with history, connection, and emergent beauty. Following this awe, there can be a deep sense of humility. We are, in this story, not the masters of the universe, but a very recent and very powerful participant in a system that is vastly older, larger, and more complex than ourselves. Our intelligence is remarkable, but it is a young intelligence. The planet has a different kind of wisdom, a deep, systemic wisdom encoded in its feedback loops and its biodiversity. This perspective gently decenters the human story. It reminds us that we are just one thread in a magnificent tapestry, and that the tapestry's integrity does not depend on our dominion, but on our integration. This humility can then blossom into a feeling of gratitude. It is a gratitude for the unearned gifts of the system, the stable climate, the clean water, the fertile soil. These are not commodities to be exploited. They are the baseline conditions for our existence, provided freely by the workings of the planet. To see the world this way is to feel a sense of being profoundly provided for. This feeling is not passive. It is an active appreciation that can inspire a desire to care for the systems that care for us. Finally, this emotional reframing can lead to a sense of calm and belonging. The anxieties of our individual lives, the pressures of our human world, can feel all-consuming. But when we place them against the backdrop of geological time and planetary processes, they can shrink to a more manageable size. This is not to diminish our struggles, but to contextualize them. We are part of something immense, resilient, and enduring. To feel your own life as part of this grand 4-billion-year-old story of continuity and adaptation can be deeply reassuring. It is the feeling of coming home, of knowing your true place, of belonging not just to a family or a nation, but to a planet. The intellectual model becomes a source of quiet strength, a bedrock of meaning in a turbulent world. Our journey has taken us through the realms of science, geology, biology, physics, and chemistry. We have used data, models, and evidence to build a picture of our world. But every journey of knowing eventually reaches a boundary, a place where the data stops and the search for meaning begins. It is important to acknowledge this philosophical boundary and to hold the questions it raises with a gentle, open curiosity. The scientific story we have told is a story of how. It explains the mechanisms, how the carbon cycle works, how the moon stabilizes the Earth's tilt, how photosynthesis changed the atmosphere. It is a powerful and satisfying story, but it does not and cannot answer the question of why. Why this universe? Why a planet with these particular properties? Why the emergence of life and consciousness? Science can describe the path that was taken, but it cannot explain why that path existed in the first place. This is where science gives way to philosophy, spirituality, and personal meaning-making. When we are confronted with the sheer, improbable fine-tuning of the universe and our planet for life, we are faced with a choice of interpretation. Is it, as the strict materialist view might suggest, simply a matter of cosmic luck, a statistical inevitability in an infinite or near-infinite universe? Are we simply the winners of a lottery so vast that a winning ticket was bound to be drawn somewhere, sometime? This is a coherent and intellectually honest position. It requires no faith, only an acceptance of the power of chance and scale. Or does the intricate, life-sustaining order we observe point to something more? Does it suggest a deeper principle of organization or creativity at work in the cosmos? This is not necessarily to invoke a traditional personified creator. It could be an impersonal, emergent tendency toward complexity and consciousness, a creative urge inherent in the fabric of reality itself. This view sees the universe not as a random collection of particles, but as a story unfolding, a process with a direction, even if that direction is not guided by a conscious mind. And then there are the more traditional religious or spiritual interpretations, which see the order and beauty of the world as a direct expression of a divine intelligence or a sacred presence. In this view, the scientific story of how is not a contradiction of the spiritual story of why, but a revelation of its breathtaking scope and detail. The laws of physics are the grammar of the divine language. The 4 billion-year history of life is the epic poem being written. Our exploration does not and should not try to provide a verdict on these ultimate questions. It simply brings us to the shoreline of this great ocean of mystery. The purpose of our scientific journey is to give us a clearer view of the ocean, to help us appreciate its depth and its vastness. What we make of that view, what meaning we draw from it, is a deeply personal act of interpretation. The data can take us no further. From here, we must rely on our other human capacities, our intuition, our sense of wonder, and our search for a meaningful place in the cosmos. The boundary is not a wall, but an invitation to a different kind of inquiry, one that we each must undertake for ourselves. As we stand at this philosophical boundary, two grand frames for interpreting the order we see often present themselves: design versus emergence. These two ways of seeing the world can seem to be in conflict, but if we approach them with humility, they can lead to a similar place of awe and wonder. The first frame, the idea of design, is ancient and intuitive. When we see something complex, functional and beautiful like a watch or a painting, we naturally infer the existence of a designer, a watchmaker, or an artist. When we look at the world with its intricate ecosystems, its elegant physical laws, and the breathtaking complexity of a single living cell, it is easy to apply the same logic. The world looks like it has been designed. This is the heart of the teleological argument for the existence of a creator. In this frame, the order we see is a product of a pre-existing intelligence. The plan came first, and the execution followed. The universe is a deliberate creation. The second frame, the idea of emergence, is more recent, arising from the study of complex systems. In this view, the order we see is not imposed from the top down by a designer. Instead, it arises from the bottom up, from the interactions of many simple components following simple rules. A flock of starlings creates its beautiful, coordinated aerial dance without a leader or a choreographer. Each bird is just following a few simple rules like stay close to your neighbors but don't collide. The complex, graceful pattern of the flock is an emergent property of these simple, local interactions. In this frame, the universe is a grand emergent process. The fundamental laws of physics are the simple rules. The particles of matter and energy are the simple components. Over billions of years, the interactions of these components have given rise to stars, galaxies, planets, and, on at least one planet, life. Life itself is an emergent phenomenon, and consciousness is an emergent property of a certain kind of complex biological network. The order we see is not a pre-existing plan being executed. It is a creative process of self-organization, constantly discovering new forms and new possibilities. At first glance, these two frames seem irreconcilable. One posits a mind-first universe, the other a matter-first universe, but what if we hold them in parallel? Both frames are attempts to explain the same astonishing fact, that the universe is not just a chaotic, random mess. It is a place of profound and beautiful order. Both frames, when followed to their conclusion, lead to a deep sense of wonder. The design frame leads to wonder at the mind of the designer. The emergence frame leads to wonder at the incredible creative potential latent within matter and energy itself. Perhaps the distinction is not as sharp as we imagine. Is a universe that has the inherent capacity to give rise to consciousness and beauty from its own substance any less wondrous than one that was designed by a pre-existing consciousness? Both paths lead us to confront a reality that is far more mysterious and magnificent than our everyday experience would suggest. Whether we call the source of this order God, or the laws of nature, or the principle of emergence, our response can be the same: a humble and grateful recognition that we are part of something extraordinary. The two frames can be seen not as competing answers, but as two different languages trying to describe the same ineffable truth. And so we bring our awareness back one last time to this room, to this moment, to you. After this long journey through the vastness of space and time, the final step is to locate yourself, your own embodied presence, right in the center of the system we have explored. You are not merely an observer of this system, you are a component of it. The boundary between you and the Earth system is a porous and arbitrary line. Consider your skin. It seems like a clear boundary separating you from the world. But it is a permeable membrane constantly exchanging gases and moisture with the atmosphere. It is populated by a rich ecosystem of microbes, your microbiome, that is essential to your health. Your skin is not a wall, it is a dynamic interface. Consider your breath. With every inhalation, you are bringing the outside world deep into your body. You are taking in molecules that were, just recently, part of a tree, or the ocean, or the breath of another being. With every exhalation, you are releasing a part of yourself back into the world. Your breath is a physical manifestation of your inseparability from the planetary whole. You are in a constant, rhythmic, and intimate conversation with the atmosphere. Consider your body itself. The atoms that make up your bones, your muscles, your brain were not created for you. They were forged in the heart of long-dead stars. Billions of years ago, they have been cycling through the Earth's systems for eons. You are borrowing them. You are a temporary, self-organizing pattern in a river of ancient matter. You are the universe for a brief and precious time, made conscious of itself. This "you are in the loop" framing is the ultimate translation of our entire exploration. It is the felt sense of personal belonging. It moves the idea of the Earth system from an abstract concept in your head to a lived reality in your body. This brings with it a subtle but powerful form of agency. If you are part of the system, then your state of being affects the system, however minutely. Your own health is a reflection of the health of the local ecosystem you are embedded in. The choices you make about what you eat, how you move, what you pay attention to, these are not just personal choices. They are your way of participating in the great conversation. This is not a call to a frantic, anxious sense of responsibility. It is the opposite. It is a release from the illusion of separation. It is an invitation to feel the deep, quiet support of the vast system that holds you, that breathes through you, and that you are an expression of. You are not a stranger here. You belong to this place as surely as a wave belongs to the ocean. So, where have we been tonight? We began with a single, gentle question. What if we lived on the sun? We used this impossible premise not as a destination, but as a lens. By imagining a world without buffers, a world of pure, unmediated energy, we began to see the quiet, intricate, and often invisible systems that make our own world a sanctuary of stability. We journeyed from the simple, human-scale buffers of shade and the daily rotation to the complex atmospheric feedbacks that act as the planet's thermostat. We saw how the gravitational dance with our moon has provided a deep, long-term stability for our climate, and how the Earth's own geology holds an archive, a memory of its past trials and recoveries. We explored the profound agency of life itself, from the microbes that built our atmosphere to the forests that make their own rain, discovering that life is not a passenger on Earth, but a co-creator of it. We zoomed out to the slow tectonic waltz of the continents and zoomed in to the fundamental energy budget that governs it all. We paused to consider other ways of knowing, from ancient myths to the strongest skeptical counter-arguments. We wrestled with the limits of our knowledge and the biases inherent in our detective work. Then we made the turn, dissolving the simple binaries and embracing a more holistic, interconnected view of a planet that is not just habitable, but that actively participates in its own ongoing creation. We synthesized these threads into a single, emergent story of a multi-layered, self-regulating system. And now we end where we began, but perhaps with a new perspective. The question, what if we lived on the sun, no longer seems like an abstract fantasy. We now have a deeper appreciation for what it means to live here, on Earth, in this buffered, mediated, and profoundly graceful world. We have, in a sense, come home. As our time together draws to a close, I want to extend a quiet and sincere thank you. Thank you for being here. Thank you for lending your curiosity and your attention to this shared journey. In a world that so often demands our frantic energy, the simple act of setting aside time to rest, to wonder, and to learn is a small but radical act of peace. You are part of a community of listeners, all seeking a moment of calm in our own corners of the world. There is a quiet strength in knowing that we are not alone in this desire for a deeper, more thoughtful connection with the world around us. If this journey has been a source of comfort or gentle insight for you, we would be honored if you would share it with others who might also benefit from a quiet hour of wonder. There is no urgency in this invitation. The most important thing is that you feel rested and at ease. Your presence here has been the only thing required. So thank you truly for spending this time with us. And so we let our central question dissolve. There are no final answers to hold on to, no conclusions to memorize. The purpose of our journey was not to arrive at a destination, but to cultivate a certain quality of attention, a way of seeing the world with a little more wonder, a little more humility, and a deeper sense of belonging. The vast planetary systems we have explored are still at work, as they have been for eons. The slow grind of the tectonic plates, the great circulation of the oceans, the silent, life-giving chemistry of photosynthesis, all of this continues, indifferent to our awareness of it, yet providing the very foundation for it. Our understanding does not change the system, but it can change our relationship to it. It can transform our experience from one of alienation to one of intimacy. Let the complexity we have explored become a source of comfort, not anxiety. The world is not a fragile, perfect machine that we are in danger of breaking. It is a tough, resilient, and adaptive system that has weathered catastrophes far greater than any we have yet faced. This does not absolve us of our responsibility, but it frames that responsibility in a context of hope and potential. We are part of that resilience. Our creativity, our consciousness, our capacity for care, these are not separate from the Earth's systems. They are some of its newest and most potent tools, so let your mind be still. Let the weight of these ideas settle. There is nothing more to do, nothing more to figure out. All that is left is to rest, held in the quiet, stable cradle of a planet that has been perfecting the art of stability for 4 billion years. Let the curiosity remain, but let it be a soft, sleeping curiosity, content to wait for a new day. As you lie here, on the edge of sleep, bring your awareness back to the simplest, most immediate sensations. The feeling of the air in the room, perhaps it is cool, a gentle reminder of the Earth's nightly exhalation into the cold of space. The darkness behind your eyelids is the shadow of the Earth itself, a planetary shield that has turned you away from the brilliant gaze of the sun, offering this moment of respite and peace. Think of the materials that surround you. The wood in the floor or the walls, once a living tree, a testament to the quiet, patient process of turning sunlight and water into substance. The cotton in your sheets, a soft, fibered gift from a plant that, like all plants, participates in the great atmospheric conversation. Even the metal in the wiring of your home or the glass in your window was once rock, part of the slow geological memory of the planet. You are resting inside a mosaic of the very systems we have explored. A faint beam of moonlight might fall across the room, illuminating a slow, gentle dance of dust motes in the air. Each mote is a tiny piece of the world, a particle of soil, a speck of pollen, a flake of your own skin. For a moment they are made visible, caught in a borrowed light from a celestial body whose gravitational presence has helped to make our world calm and predictable. In that simple, quiet image, the cosmic and the mundane, the vast and the microscopic, all meeting in the stillness of your room, our entire journey is reflected. You are here. You are held. and you can rest now.